At a certain height above our planet, the world you know begins to fade. The sky shifts from calm blue to a deep, endless darkness. The air becomes so thin that even the loudest shout would barely move. Clouds fall away beneath you, stars sharpen above you, and the laws of nature start to behave in strange, unfamiliar ways. This is the edge of space, the silent border between Earth and the vast unknown. It is a place few humans have ever reached, yet it affects life down here every second. Satellites glide through this thin boundary, mysterious lights appear and vanish without warning, and invisible forces sweep through it with unbelievable power. Scientists call it a frontier, explorers call it a challenge. But to many it remains one of the greatest secrets still untouched. What happens there? What hides in that quiet strip where our world ends and something far greater begins? Before we begin, let us know where in the world you're watching from and what the time is for you now. Drop it down in the comments below and settle in for a fascinating journey to the edge of space. To truly understand the amazing discoveries made by the James Webb Space Telescope, also called JWST, we first need to go all the way back to the very beginning of everything, the birth of the universe. This incredible moment is called the Big Bang. But don't think of a normal explosion like fireworks or a bomb. The Big Bang was completely different. It was the sudden and incredibly fast expansion of the universe from a single point that was unimaginably small, extremely hot, and full of energy. This event happened about 13,800 million years ago, and it wasn't just the start of the universe, it was when space, time, and all matter came into being. In the first few seconds after the Big Bang, the universe was like a storm of energy, filled with tiny particles moving in every direction. It was so hot, hotter than anything we can imagine, with temperatures reaching trillions of degrees, that atoms couldn't even form. Everything was pure chaos, with no stars, no planets, and no galaxies, just glowing, blinding energy. For hundreds of millions of years, the universe stayed in this strange state. Slowly it expanded and cooled down. Then, something amazing happened. Around 400 million years after the Big Bang, the first atoms came together, mostly hydrogen and helium. These simple gases were pulled together by gravity, and as they clumped, they heated up and created the very first stars. These new stars didn't shine alone. They came together to form the first early galaxies, lighting up the darkness of space and starting what scientists call the cosmic dawn. This was a key time when the universe began forming its first structures, and this is exactly the moment the James Webb Space Telescope is now looking at. It is taking breathtaking pictures and collecting important data from when the first galaxies were just starting to shine, helping us understand the universe's earliest days. The James Webb Space Telescope is unlike anything humans have ever built. It was launched into space on the 25th of December, 2021, a cosmic Christmas gift for humanity. But JWST doesn't orbit the Earth like most satellites. Instead, it travels around the Sun, staying at a special point called the Second Lagrange Point, or L2. This point is about 1 million miles from Earth. It was chosen so the telescope could stay steady and far from Earth's heat and light, giving it a clear view of the universe. What makes JWST truly special is its ability to see the universe in a type of light our eyes cannot detect, infrared light. While visible light is blocked by clouds of space dust, infrared light can pass through, showing hidden stars, galaxies, and other objects that other telescopes cannot see. This is very important for studying the oldest and farthest objects in space. As the universe expands, the light from faraway galaxies gets stretched into longer, redder wavelengths. This stretching, called the cosmological redshift, turns visible light into infrared light. Because JWST can detect this faint, stretched infrared glow, it can look farther into space and back in time than any telescope before it. It's like having a time machine showing us the universe more than 13,500 million years ago, just a few hundred million years after everything started. When JWST sent back its first images, scientists were amazed. The telescope had looked deep into the ancient past and captured pictures of galaxies forming only a few hundred million years after the Big Bang. This was the universe's baby stage, and yet it was already full of surprises. Astronomers expected to find only a few small galaxies, but they found many more than they had imagined. These early galaxies came in all kinds of strange shapes and sizes, very different from what scientists expected. It turned out that the early universe was more active, crowded, and chaotic than anyone had guessed. One of the most exciting things JWST discovered was proto-galaxies. These were the first clumps of stars that would later grow into the huge galaxies we see today. But they didn't look neat or orderly. Instead of smooth spirals or round shapes, these early galaxies were messy, clumpy, and wild. New stars were being born at an incredible speed, with entire clusters lighting up in bursts of energy. This showed that galaxy formation was not slow and gentle, but full of energy and drama, changing how we understand the universe's growth. JWST also helped scientists get closer to finding the very first stars ever formed, called Population 3 stars. These stars were unlike anything we see today. They were made from the simplest materials left by the Big Bang, mostly hydrogen and helium, without heavier elements like carbon or oxygen. Because of this, scientists believe these stars were huge, much bigger than our Sun, and burned extremely hot and bright. But they lived fast and died young, burning their fuel quickly and exploding in massive blasts called supernovae. Some of these explosions were so powerful they became rare events called pair instability supernovae, the strongest explosions in the universe. When these ancient stars exploded, they spread heavier elements into space, which later helped form new stars, planets, and even the building blocks of life. By studying these ancient giants, scientists are slowly solving the mystery of how the universe grew from simple beginnings into the complex place we live in today. But JWST doesn't only look at the distant past. It is also helping scientists study two of the biggest mysteries in the universe: dark matter and dark energy. These strange forces make up about 95% of everything in the universe, but we cannot see or touch them. Dark matter doesn't shine or give off light, but we know it exists because of how it pulls on galaxies with its strong gravity. JWST helps detect dark matter by watching how it bends light from galaxies behind it, a trick of nature called gravitational lensing. This lets astronomers map where dark matter might be and understand how it shapes the universe. Then there's dark energy, which is even more mysterious. It's a force that makes the universe expand faster and faster. By measuring how quickly galaxies move away from us, JWST gives scientists new clues about dark energy. These discoveries are very important because they might help answer a huge question. Will the universe keep expanding forever, or will it eventually stop and collapse? JWST is also searching for something closer to home: life beyond Earth. One of its most exciting missions is to study planets outside our solar system, called exoplanets. Some of these distant worlds might have the right conditions to support life. Using its advanced tools, JWST can examine the gases in a planet's atmosphere and look for chemical signs that might hint at life. If it finds water vapor, that could mean the planet has clouds or even rain. If it finds methane, it might come from volcanoes, or maybe even microbes. If it finds lots of oxygen, scientists will start to wonder, could there be plants or alien life producing it? The moment we find proof we're not alone would change everything we thought we knew. However, the James Webb Space Telescope is more than just a camera in space. It is a window into the deepest mysteries of time and space. It has already confirmed some theories and overturned others. One of its most surprising discoveries is that fully formed galaxies appeared much faster than anyone expected. According to older ideas, it should have taken billions of years for galaxies to slowly grow. But JWST is showing us galaxies that came together in a cosmic blink of an eye. This means scientists may need to rewrite major parts of our understanding of the universe. One of the most astonishing discoveries made by the James Webb Space Telescope involves the enormous black holes found at the hearts of some of the oldest galaxies ever observed. Scientists used to think that these black holes had to be relatively small, simply because there had not been enough time in the early universe for them to grow so massive. But the James Webb Space Telescope has revealed black holes that are far larger than anyone expected. This shocking finding suggests that black holes might form and expand much faster than scientists had ever imagined. It challenges everything we thought we knew about how black holes are born and how they develop over time. These surprising results remind us that the universe still holds countless secrets, and thanks to the incredible capabilities of the James Webb Space Telescope, we're only beginning to uncover them. To truly appreciate these discoveries, we need to look closer at the amazing machine behind them. The James Webb Space Telescope, often called JWST, is one of the most advanced instruments humanity has ever sent into space. Its enormous mirror, covered in gold, stretches more than 21 feet across, roughly the size of a small house. This mirror was designed to collect the faintest rays of infrared light coming from galaxies billions of light years away. What makes it even more remarkable is that the mirror is not one single piece. Instead, it is made of 18 golden hexagon-shaped segments. These segments unfolded in space like petals, forming a stunning pattern that resembles a giant golden flower opening in the darkness. But JWST's power goes far beyond its mirror. It carries advanced instruments, including powerful cameras and spectrographs, which do much more than take pictures. They can break down the light from stars and galaxies that are millions or even billions of light years away, allowing scientists to learn what these stars are made of, how they move, and how old they are. In a way, it is like digging through ancient ruins, but instead of soil and stones, scientists are reading the history of the universe written in light that has travelled across space for billions of years. The James Webb Space Telescope is not just an engineering marvel, it is also a symbol of global cooperation. While NASA, the space agency of the United States, led the project, two other major partners were crucial in making it a reality: the European Space Agency and the Canadian Space Agency. The European Space Agency contributed key scientific instruments, while the Canadian Space Agency added high-tech tools and funding to support the mission. This partnership shows what humanity can achieve when we work together. Scientists, engineers, and dreamers from all corners of the world joined forces to build something truly extraordinary. JWST proves that when people unite around a shared goal, like exploring the universe, we can achieve discoveries beyond what anyone thought possible. Looking at what JWST has already revealed, it is impossible not to feel excited about the future. The telescope is collecting so much valuable data that scientists will be studying it for many decades. These discoveries will inspire new generations of astronomers and scientists to continue asking questions and pushing the limits of human knowledge. And JWST is only the beginning. In the coming years, other remarkable space missions will launch. The Nancy Grace Roman Space Telescope, for example, will give us an even wider view of the universe, while the European Extremely Large Telescope, being built on Earth, will provide incredibly sharp views of distant galaxies. Together, these tools will help humanity uncover more secrets about the cosmos, how it began, how it works, and how we fit into the grand story of the universe. These missions are about more than science. They're about human curiosity, the desire to understand where we came from, and the deep connection we feel to the stars above. Every project like JWST brings us closer to the universe and to one another. The James Webb Space Telescope has already changed the way we see the universe. By looking back more than 13,500,000,000 years into the past, it allows us to see the cosmos as it appeared just after the Big Bang, giving us a glimpse of the universe's earliest moments and the beginnings of everything we know. The atmosphere surrounding our planet is like a vast invisible blanket stretching far above us and protecting life on Earth. It is not a simple, uniform layer of air. Instead, it is made up of several distinct layers, each with its own characteristics, purposes, and surprises. Understanding these layers helps us see how Earth functions, how life survives, and even how humans can explore space. These layers are known by specific names: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is unique, with its own temperature changes, air pressures, and functions, and each plays a vital role in sustaining life on our planet. Closest to the ground is the troposphere, which is the layer we live in and experience every day. It stretches from the Earth's surface up to about 7 to 20 kilometers above sea level, depending on whether you're at the poles or the equator. Near the poles, it is thinner, reaching around 7 kilometers, while near the equator it can extend up to 20 kilometers because the air is warmer and expands more. This layer contains nearly 75% of all the air in the atmosphere, and nearly all water vapor, clouds, and weather phenomena occur here. The troposphere is the dynamic, ever-changing layer of life, where winds blow, storms form, and birds soar. Temperature in the troposphere decreases steadily with altitude. On average, for every 1 kilometer you go higher, the temperature drops by about 6.5 degrees Celsius. This is why mountaintops are so cold and why the air becomes thinner the higher you climb. This is why mountaintops are so cold and why the air becomes thinner the higher you climb. The troposphere is heated primarily from the ground up rather than from above, which means the sun warms the Earth's surface, and this warmth then radiates into the air. The weather, as we know it, is a product of this layer's unique characteristics. Thunderstorms, tornadoes, hurricanes, and gentle rains are all created in this layer. Planes that fly at high altitudes generally cruise near the top of the troposphere because it is stable and provides less resistance than lower down in the layer. Above the troposphere is the stratosphere, which stretches roughly from 20 kilometers to 50 kilometers above the Earth. This layer is calm and stable, with very little turbulence, unlike the roiling, weather-filled troposphere below. One of the most important features of the stratosphere is the ozone layer, a thin but crucial layer of oxygen molecules that absorbs the sun's harmful ultraviolet radiation. Without this layer, life on Earth would be exposed to dangerous levels of radiation, leading to increased risks of skin cancer, cataracts, and damage to plants and animals. The stratosphere's temperature behaves differently from the troposphere. Instead of cooling with height, the temperature gradually increases because the ozone absorbs the sun's energy. This warming effect makes the stratosphere more stable and allows jet streams, powerful rivers of air, to flow smoothly. Planes that fly long distances, especially commercial jets, often fly in the lower stratosphere to avoid weather turbulence and to take advantage of these fast-moving air currents. Rising higher still, we enter the mesosphere, which extends roughly from 50 kilometers to 85 kilometers above the Earth. This layer is colder than the ones below it and is actually the coldest layer in the Earth's atmosphere, with temperatures dropping to as low as -90 degrees Celsius. The mesosphere is a place of extremes, where the air becomes very thin and it is extremely difficult for human-made aircraft to operate. This is also the layer where most meteors burn up upon entering the Earth's atmosphere, creating the bright streaks of light we call shooting stars. Because of its thin air and low temperatures, it is one of the least studied layers, as it is too high for planes and too low for spacecraft. Scientists rely on specialized rockets and satellites to gather information from this region. The mesosphere acts as a protective shield, stopping many space rocks from reaching the Earth's surface and causing damage. Above the mesosphere is the thermosphere, which stretches from about 85 kilometers to 600 kilometers above the Earth. In this layer, temperatures rise dramatically with altitude, reaching hundreds and even thousands of degrees Celsius. However, despite these extremely high temperatures, this layer would not feel hot to a human because the air is so thin that there are very few molecules to transfer heat. The thermosphere is also where the auroras, the northern and southern lights, appear. These dazzling light shows occur when charged particles from the sun collide with gases in this layer, creating brilliant greens, reds, and purples that dance across the polar skies. The thermosphere also plays a crucial role in communication. It contains the ionosphere, a region full of charged particles that reflect radio waves back to Earth, enabling long-distance radio communication. Satellites orbit within this layer, as it provides enough resistance to maintain their path while being above most of the Earth's atmosphere. Astronauts aboard the International Space Station live and work in the lower part of the thermosphere, experiencing an almost direct view into space while still being protected by Earth's atmosphere. Finally, the outermost layer of the atmosphere is the exosphere, which begins around 600 kilometers above the Earth and gradually fades into the vacuum of space. In this layer, air molecules are so sparse that they can travel hundreds of kilometers without colliding with one another. The exosphere acts as a transitional zone between the Earth and outer space. Hydrogen and helium are the primary gases here, and because of the extremely low density, particles can escape into space. Satellites, especially those in geostationary orbits, are located in this layer, as it provides a stable environment with minimal atmospheric drag. The exosphere is the frontier of Earth's atmosphere, where the planet's protective layer gives way to the infinite emptiness of space. Each layer of the atmosphere not only serves its own purpose, but also interacts with the layers above and below it. The troposphere, with its storms and winds, depends on the stable stratosphere above it to keep weather patterns organized. The mesosphere protects us from meteors, while the thermosphere shields us from harmful solar radiation and enables advanced technology. Even the exosphere, almost like the thin breath of the planet, marks the boundary where Earth's influence ends and space begins. The atmosphere as a whole works like a finely tuned machine, supporting life, protecting the planet, and enabling exploration beyond our world. To truly appreciate the atmosphere, we must also consider how it affects daily life. The troposphere shapes our weather, from gentle breezes to powerful hurricanes. The stratosphere's ozone layer protects our skin and eyes from dangerous rays. The mesosphere ensures that space debris mostly burns up before reaching us. The thermosphere makes satellite communication and GPS possible, and the exosphere provides a safe zone for space travel. Every time we look up at the sky, see clouds, watch the northern lights, or track a satellite, we are witnessing the incredible work of these layers. The atmosphere is also not static. Human activity, such as pollution and emissions, can affect the delicate balance in each layer. The thinning of the ozone layer in the stratosphere due to chemical pollutants has been a serious concern for decades. Global warming primarily affects the troposphere, changing weather patterns, melting glaciers, and influencing life across the planet. Understanding how each layer functions allows scientists to predict and mitigate these impacts, helping humanity live more sustainably on Earth. Historically, humans only began to understand the atmosphere in a detailed way in the last few centuries. In the 17th century, early experiments with air pressure and gases revealed that the atmosphere had weight and density. By the 19th century, scientists had begun measuring the different layers using balloons and early forms of rockets. With the development of modern satellites in the 20th century, our understanding expanded dramatically, allowing us to study the thermosphere and exosphere directly from space. Today, weather forecasting, satellite technology, and space travel all rely on our knowledge of these atmospheric layers. Each layer has a distinct personality. The troposphere is active and ever-changing, full of life and motion. The stratosphere is calm and protective, silently safeguarding life below. The mesosphere is mysterious and harsh, a cold and dangerous barrier against the threats from space. The thermosphere is vibrant and radiant, a place where energy and light from the sun collide in dazzling displays. The exosphere is distant and lonely, marking the edge of our planet's influence and the beginning of the unknown universe. Together, these layers form a continuous, complex and beautiful system, one that we depend on for life, weather, communication, and exploration. Even simple activities like flying in an airplane or sending a text message depend on the atmosphere's layers. The plane cruises in the upper troposphere or lower stratosphere, taking advantage of smooth airflow. The text message may travel through satellites orbiting in the thermosphere or exosphere, bouncing through the ionosphere on its journey back to Earth. The auroras we admire on a winter night, the protective shield of ozone above our heads, and even the meteors streaking across the sky on a clear night, all are products of these layers working in harmony. Scientists continue to explore and study these layers, using advanced satellites, high-altitude balloons, rockets, and even the International Space Station to gather data. Each discovery brings a deeper understanding of how Earth functions, how life is supported, and how humans might one day travel safely beyond our planet. The atmosphere is not just a layer of air, it is a living, dynamic system, constantly changing, adapting, and protecting the Earth. The universe surrounding Earth is filled with invisible forces that are both fascinating and dangerous. Among the most mysterious of these forces are cosmic rays and solar radiation. They are invisible to the eye, yet they travel across space with enormous energy, and have the power to affect everything from tiny living cells to the technology humans rely on. Cosmic rays come from deep space, far beyond the solar system, while solar radiation is produced by the Sun, the star at the center of our solar neighborhood. Both of these forms of radiation travel across millions, even billions of kilometers before reaching Earth, and they carry the power to change matter in ways that are often subtle and sometimes harmful. Cosmic rays are made up of high-energy particles that move faster than almost anything else in the universe. They consist mostly of protons, which are tiny particles that make up the cores of atoms, along with heavier atomic nuclei and electrons. These particles are accelerated to incredible speeds by massive cosmic events, such as exploding stars known as supernovae, or by even stranger phenomena near black holes and neutron stars. Some cosmic rays come from distant galaxies, crossing vast cosmic distances to eventually reach Earth. The energy they carry is extraordinary. A single particle can have more energy than the most powerful particle accelerators built on Earth. Despite their small size, cosmic rays carry enough energy to penetrate deep into materials, including human tissue, electronics, and spacecraft. The journey of cosmic rays to Earth is not simple. Space is filled with magnetic fields, both from our galaxy and from other sources in the universe. These magnetic fields bend and twist the paths of cosmic rays, scattering them in many directions. This makes it difficult to trace exactly where a particular cosmic ray originated. When they finally approach Earth, most of these particles collide with atoms in the upper layers of the atmosphere. These collisions create showers of secondary particles that spread out and reach lower layers of the atmosphere. Some of these particles even reach the ground, though by the time they arrive, they have lost much of their original energy. Despite this weakening, the effects of cosmic rays on living organisms and technology are significant. Solar radiation, on the other hand, originates from our Sun. The Sun is a massive ball of hot gas, mostly hydrogen and helium, and it produces energy through a process called nuclear fusion. In this process, the Sun's core fuses hydrogen atoms into helium, releasing enormous amounts of energy. Some of this energy is emitted as visible light, which illuminates the planet and sustains life. However, the Sun also produces other types of radiation, including ultraviolet rays, X-rays, and a continuous stream of charged particles known as the solar wind. These particles, although less energetic than cosmic rays, are still powerful enough to affect Earth's atmosphere and magnetic field. One of the most dangerous aspects of solar radiation comes from sudden eruptions on the Sun's surface, known as solar flares and coronal mass ejections. Solar flares are intense bursts of radiation, while coronal mass ejections release massive clouds of charged particles into space. When these clouds reach Earth, they can interact with the planet's magnetic field and atmosphere, causing geomagnetic storms. These storms can disrupt satellite communications, navigation systems, and even electricity grids. In extreme cases, solar storms have the potential to cause widespread technological failures. Beyond their technological impact, these eruptions also increase the levels of radiation that reach astronauts and high-altitude flights, presenting a real risk to human health. Radiation from both cosmic rays and the Sun can damage living cells. This happens because the high-energy particles can knock electrons off atoms, a process known as ionization. When this occurs inside human tissue, it can damage DNA and other vital molecules. Over time, repeated exposure to ionizing radiation increases the risk of cancer and other health problems. The human body has natural defenses, including repair mechanisms for damaged DNA, but these defenses are not perfect. Long-term exposure, such as that experienced by astronauts in space, can be particularly dangerous. For example, astronauts traveling beyond Earth's protective magnetic field are exposed to higher doses of cosmic radiation, which can increase their risk of cancer, cataracts, and other health issues. Earth itself has natural shields against these invisible hazards. The atmosphere acts as a thick blanket, absorbing much of the incoming radiation. The magnetic field of the planet, generated by movements of molten iron in the core, also plays a critical role. It deflects charged particles from the solar wind and cosmic rays, funneling some toward the polar regions, where the particles interact with the atmosphere to create phenomena such as the auroras. Without these protections, life on Earth would be exposed to much higher levels of radiation, making survival far more difficult. Even so, small amounts of cosmic and solar radiation penetrate these defenses and reach the surface, which is why radiation is a natural part of life on Earth, though usually at safe levels. Scientific instruments and satellites have allowed humans to study cosmic rays and solar radiation in great detail. Detectors on the ground, in the atmosphere and in space have measured the energy, composition, and frequency of these particles. These studies have revealed patterns and cycles, such as the 11-year solar cycle, during which solar activity increases and decreases in a predictable rhythm. At the peak of this cycle, the Sun produces more flares and solar storms, increasing the amount of radiation reaching Earth's atmosphere. Cosmic rays also show variation over time, influenced in part by the Sun's activity. During periods of high solar activity, the stronger solar magnetic field can shield Earth from some cosmic rays, reducing the number of particles that reach the planet. Cosmic rays have also been studied for their impact on Earth's climate. Some researchers have suggested that cosmic rays can influence the formation of clouds by helping tiny water droplets form around charged particles in the atmosphere. Clouds, in turn, affect the amount of sunlight that reaches Earth's surface, potentially influencing climate patterns. Although the exact role of cosmic rays in climate is still a subject of scientific debate, the interaction between these invisible particles and the atmosphere demonstrates just how interconnected space and life on Earth really are. Beyond their influence on health, technology, and climate, cosmic rays and solar radiation also serve as tools for scientific discovery. Cosmic rays have helped physicists understand fundamental particles and forces. In the mid-20th century, cosmic rays were instrumental in the discovery of particles such as the muon and the pion, long before powerful particle accelerators were available. These discoveries provided critical insights into the building blocks of matter and the forces that govern the universe. Solar radiation too has offered insights into the physics of the sun and the processes that power stars. Observing the sun's radiation in different wavelengths, from radio waves to X-rays, has allowed scientists to map the sun's surface, understand its magnetic field, and predict solar storms that might affect Earth. In addition to scientific study, cosmic rays and solar radiation pose practical challenges for human exploration of space. Astronauts venturing beyond the protection of Earth's magnetic field face exposure to higher levels of radiation, which can be harmful over time. Missions to the Moon, Mars, and beyond must take radiation into account when designing spacecraft and planning the duration of missions. Shielding materials, careful mission planning, and monitoring of solar activity are all critical strategies to protect astronauts. Even for passengers on high-altitude flights, particularly those travelling near the poles, there is a small increase in exposure to radiation from cosmic rays and the sun. Airlines and space agencies monitor these levels carefully to ensure safety. The study of cosmic rays and solar radiation has also revealed surprises about the universe. Some cosmic rays are so energetic that they challenge existing theories about how particles can be accelerated to such speeds. The most powerful cosmic rays carry energy millions of times greater than the particles produced by the largest human-made accelerators. Understanding where these particles come from and how they gain such energy remains one of the great mysteries of astrophysics. Similarly, solar radiation occasionally produces events that are far more powerful than scientists expect, leading to new discoveries about the behavior of the sun and the processes taking place on its surface. Over the years, humans have developed ways to monitor and predict the hazards posed by cosmic rays and solar radiation. Space weather forecasts based on observations of the sun and cosmic activity help protect satellites, astronauts, and even power grids on Earth. These forecasts are becoming increasingly important as technology becomes more advanced and more dependent on satellites. A strong solar storm could damage communications, navigation, and even the electrical systems that keep cities running. Understanding cosmic rays and solar radiation, therefore, is not just a matter of curiosity. It is essential for protecting modern society. Even though cosmic rays and solar radiation are invisible, their presence can be felt in many ways. They leave traces in the atmosphere, affect the behavior of particles, and interact with living cells. Scientists continue to study them using advanced detectors on Earth and in space. Instruments like the Alpha Magnetic Spectrometer aboard the International Space Station measure the composition of cosmic rays with incredible precision, searching for signs of exotic particles and even clues about the nature of dark matter. Solar observatories, both on Earth and in orbit, monitor the sun continuously, watching for flares and eruptions that could affect life and technology on the planet. One of the most exciting and amazing discoveries in modern astronomy, and at the edge of the visible universe, is something scientists call the earliest light. This isn't just ordinary light. It's a soft, ancient glow coming from some of the very first galaxies that formed only about 200 million to 300 million years after the Big Bang. Can you believe it? That light has been travelling across space for more than 13 billion years before finally reaching us. It's like getting a look at the very first chapter of the universe's story, a time when everything we know today was just beginning to form. Back in those earliest days, the universe wasn't anything like the open, starry space we see now. Instead, it was filled with a thick, hot fog made of tiny particles. This fog was so dense that light couldn't move freely. Light particles, called photons, kept bumping into other particles and scattering in all directions. It was as if the universe was covered by a giant curtain, blocking any light from passing through. But slowly, over hundreds of thousands of years, the universe began to cool down and expand. and as it expanded, the fog began to thin out. Finally, a moment came when light could escape and travel across space for the very first time. This amazing event is called the Cosmic Microwave Background, or CMB. It's a faint leftover glow that still fills the universe today, like a baby photo of the cosmos, showing us what everything looked like when the universe was still very young. Even more amazing is what happened a little later, between 200 million and 300 million years after the Big Bang. That's when the very first stars and galaxies were born. This was the moment when real starlight first started shining throughout the universe. And this starlight didn't just light things up, it changed the entire cosmos. Before this time, the universe was dark and foggy. But once the first galaxies and stars appeared, they helped clear away the remaining fog, allowing light to shine freely for the first time. This incredible change is called the Cosmic Dawn, the start of a new era when the universe lit up with stars, galaxies, and beauty. What makes this discovery so special is that the light from these very first galaxies has been travelling through space for over 13 billion years. That is an unimaginably long journey. And yet, we can still detect this ancient light today. It's like hearing a faint whisper from the dawn of time, a message that carries secrets from when the universe began forming itself. This light tells us when stars first appeared, when galaxies started to take shape, and how the universe changed from a messy cloud of particles into a structured and beautiful place. For a long time, scientists thought galaxies started forming this early, but it was very hard to prove. The farther away a galaxy is, the longer its light takes to reach us. And since these early galaxies are extremely far away, their light is also very faint by the time it gets to Earth. To make things even harder, the universe has been stretching ever since the Big Bang. As space stretches, the light moving through it stretches too, changing from short waves like ultraviolet and visible light into much longer waves like infrared, which our eyes cannot see. To find this ancient, stretched-out light, scientists needed powerful tools. They turned to some of the most advanced telescopes ever built, including NASA's James Webb Space Telescope, the Hubble Space Telescope, and some of the largest telescopes on Earth. These instruments are specially designed to detect infrared light, which we cannot see, but which holds the key to understanding the early universe. One of the biggest challenges in spotting this early light is how much it has changed. Light that was once bright and bluish, like ultraviolet, is now stretched so much that it appears red and soft like infrared. That's why infrared telescopes are so important. The James Webb Space Telescope was built specifically to detect this kind of ancient light. With it, scientists can now see things that were hidden before, events that happened just after the universe was born. This ancient light is more than just beautiful. It is extremely useful. It shows us that galaxies and stars started forming much earlier than anyone expected. This helps answer a big question. How quickly did the universe begin to organize itself after the Big Bang? The answer, thanks to this light, is much faster than we thought. The universe wasted no time starting to create stars, galaxies, and eventually everything we know. Now let's talk about some of the most mysterious stars of all, called Population 3 stars. These were the very first stars in the universe. They were nothing like the stars we see today. These stars were made almost entirely of hydrogen and helium, the two lightest and simplest elements created during the Big Bang. Unlike modern stars, they didn't have any heavy elements like carbon, oxygen, or iron. Because of this, they burned much hotter and lived shorter lives. They shone brilliantly for a short time before exploding in massive supernovae. These explosions sent energy and newly formed elements into space, helping shape the next generations of stars and galaxies. These early stars also played a key role in a huge cosmic event called reionization. This event helped make the universe clear, letting light travel freely for the first time. Without these first stars, the fog might never have lifted, and the universe would have stayed dark much longer. By studying this ancient light, scientists can also learn how galaxies formed and grew over time. In the beginning, the first galaxies were probably small and oddly shaped, messy compared to the large, beautiful galaxies we see today. But over billions of years, these galaxies collided, merged, and grew larger and more complex. This long process eventually led to galaxies like our own Milky Way. What's even more amazing is that this earliest light connects directly to two of the biggest mysteries in all science: dark matter and dark energy. These are two invisible forces that make up almost all of the universe, yet we still don't fully understand them. We can't see them or touch them, but scientists know they exist because of the strange effects they have on everything around them. Dark matter acts like a cosmic glue. It holds galaxies together, using its strong gravity to pull stars and gas into clusters. Dark energy, on the other hand, seems to be the force pushing the universe apart faster and faster. These invisible forces shape the universe every second, but quietly, without us seeing them. Here's where the ancient light becomes especially helpful. Even though dark matter doesn't shine, it still affects how galaxies move and form. The ancient light reveals those movements, like footprints in soft sand. By studying this light, scientists can trace the effects of dark matter and dark energy back to the earliest days of the universe. Every time we find more of this ancient light, it's like peeling back another layer of time. It's as if we're looking through a window into the distant past. This light began its journey billions of years ago, before our Earth even existed, before the sun was born. Now, as we observe it, we are watching the universe's first steps, as it grew from chaos into a place filled with stars and galaxies. One of the most breathtaking discoveries so far is the light coming from galaxies that formed only 200 million to 300 million years after the Big Bang. Since the Big Bang happened about 13 billion and 800 million years ago, this means we're seeing light from a time when the universe was still very young, like a newborn. These early galaxies were just beginning to form, and their light has been travelling toward us for nearly the entire age of the universe. And this is only the beginning of what we might discover. Thanks to amazing advances in technology, especially the James Webb Space Telescope, we can now see farther and clearer than ever before. These new tools are opening up parts of the universe that were once completely hidden. With every new bit of ancient light we find, we learn more about how galaxies were built, how stars were born, and how the universe slowly changed into the vast, beautiful place we call home. But this journey isn't just about stars and galaxies, it's about us. The more we learn about the early universe, about dark matter, dark energy, and the birth of stars, the more we understand our own beginnings. This ancient light doesn't just tell the story of the cosmos, it helps explain how everything we know, including our planet, our sun, and even life itself, came to be. When we look for life beyond our planet, we're not just trying to answer a science question. We're opening a door to the huge universe and asking where we truly belong. This search invites us to think about what is beyond the stars and planets we see, and what it might mean if we're not alone. Scientists who try to find life outside Earth often focus on places that might be like our world. These are places that might have liquid water, the right mix of important elements like carbon and oxygen, and steady temperatures that don't change too much. These things helped life start and survive on Earth, so they are a good place to begin when we look elsewhere. But the search is not only about finding life. It also helps us understand how rare or common life-friendly places might be in the universe. Every time we find a planet or moon with the right conditions, we get a little closer to answering the big question: is life a rare miracle, or does it happen often when the right conditions exist? If one day we do find proof of life, whether it's tiny microbes or complex creatures, it could mean that life naturally appears wherever the environment is right. That would suggest there could be many worlds in our galaxy, and even in other galaxies, where life is growing, changing, and maybe even thinking. Each discovery would help scientists better understand the many ways life might survive in strange and surprising places. It would show us how flexible life can be, and how wide the universe's possibilities might stretch. But what if we search and still find nothing? What if life is really rare or even only exists on Earth? That would also be a powerful discovery. It would make us look more closely at how life started here, billions of years ago. What were the special conditions that made Earth different? Learning that could help us understand the long chain of events that led to our own existence, and why it may be so hard to find life elsewhere. The search for alien life also makes us rethink what life even is. We might find forms of life that are so different from what we know that we don't even recognize them as alive at first. They might not need water, oxygen, or even DNA. Exploring these possibilities makes us think differently about biology, evolution, and what it really takes for something to live. It expands our view of the universe and shows that it might be far more alive and far more strange than we ever imagined. However, the search for life beyond Earth is not just about meeting aliens. It's about understanding the universe, how it works, how it changes over time, and how something as complex as life can appear, survive, and grow. It's about looking beyond our tiny blue planet and seeing the big picture of existence. Now think about something even more mind-blowing. What if there are alien civilizations out there, far ahead of us in science and technology? These civilizations, if they exist, might know things about the universe that are still unknown to us. They might have tools and machines that let them explore parts of space we can't see yet. Maybe they can detect signals or types of energy we haven't discovered. They may have been studying the universe for millions of years, gathering information and noticing patterns that we don't yet understand. With a much longer history and a better understanding of physics, they might already have answers to big mysteries we are still trying to solve, things like dark matter, dark energy, or how the universe really began. And what if they can travel between stars or even galaxies? If they can move across space like we travel across oceans, they might be gathering knowledge from distant parts of the cosmos, places we can only dream of reaching. Their discoveries could completely change how we see the universe and ourselves. These alien societies might also see the universe in very different ways, shaped by their own cultures and environments. Their ideas about time, space, or even what it means to be alive could be very different from ours. Talking with them could help us look at old questions in new ways and ask questions we never thought of. If we ever made contact with beings from another world, it could change everything. Think about it. Meeting a civilization that has been growing and learning for thousands or even millions of years. The things we could learn from them about science, life, even how to live together peacefully, could take us into a new age of discovery. We might meet new kinds of life with strange and amazing adaptations to their worlds. Their biology could be unlike anything we've seen, pushing us to rethink how life starts and survives. Their technology might seem like magic to us, but it could inspire our scientists and engineers to reach new heights. This kind of contact wouldn't just affect science. It would change our beliefs, our politics, and the way we see ourselves. Realizing we're not alone could make humanity feel more connected, less divided. We might see Earth not as many nations, but as one small world in a much bigger cosmic family. We could also learn new ways of thinking, about ethics, cooperation, fairness, and how to build better societies. These beings might have different ways of handling conflict, different ideas about justice, or even how they understand time. Talking to them could open our minds to ways of living we've never imagined. This is why the idea of contact is so powerful. It challenges what we know, sparks our imagination, and gives hope that we can grow into something greater than we are now. One of the main efforts in this search is called SETI, the search for extraterrestrial intelligence. SETI is like humanity's big ear, trying to listen across the stars for signals from intelligent life. Think of standing on a beach, with each wave representing a star. Somewhere out there, among the waves, there might be a message. SETI scientists use huge radio telescopes that scan the sky, picking up weak signals from far away. They listen for patterns or repeated sounds, clues that something intelligent might be trying to say hello. It's like tuning an old radio, trying to find a song hidden in the static. They search in many directions and for many types of signals, because any message might be coming from a planet millions or even billions of light years away. And even if it takes centuries to find one, each step brings us closer. SETI doesn't just listen for messages, it also helps us understand where life might exist and how we might talk to it. SETI researchers look at planets outside our solar system, called exoplanets, to figure out which ones might have the right conditions for life. They study how life could exist in all kinds of places, not just like Earth. SETI also makes us think about what it means to be human. If there are other beings out there, it makes us reflect on who we are, what makes us special, and how we fit into this huge star-filled universe. Above all, SETI encourages us to keep wondering, to keep exploring. It reminds us that the universe is huge and full of mystery, and we are only just starting to understand it. Maybe one day, we'll find someone out there, waiting to share the story of their world. But as we search for life in places no human has ever been, we must be careful. There are important moral questions to think about. For example, what if we accidentally bring Earth germs to another planet or moon? Even a tiny germ could harm delicate alien environments that have been untouched for billions of years. And what if we find new life or ecosystems, and people try to use them for money or power? Just like we protect natural parks and wildlife on Earth, we must treat these discoveries with care and respect. They may hold knowledge more valuable than gold, knowledge that could help us understand life, health, or the universe. We also need to think about how we act if we meet intelligent life. Do we try to talk to them? How do we do it safely without causing harm or misunderstanding? If they have their own societies and cultures, we must be careful not to disturb their natural development. The universe is unbelievably huge, stretching farther than our minds can fully understand. For thousands of years, people have looked up at the night sky, asking where it all began and how it came to be. Over the past few hundred years, scientists have worked hard to solve the mysteries of space. They've asked big questions. How did the universe start? What has happened to it over time? One of the most interesting clues to answer these questions comes from something called redshift. Though it might sound like a term from science fiction, redshift is real and very useful. It helps scientists understand how the universe has been expanding since it began. To understand what redshift is and why it matters, we first need to talk about light, the same light that comes from a flashlight or the sun. Light moves in waves, like the ripples you see when you throw a stone into a calm pond. These waves have different lengths. Some are short and some are long. The length of a light wave gives it its colour. Short waves look blue or violet, while long ones look red. Here's where it gets exciting. When scientists study light from stars and galaxies, they look closely at these waves. By measuring how long or short they are, they can learn many things, like what the object is made of, how far away it is, and even how fast it is moving. Redshift happens when the light waves stretch out as they travel through space. When the light stretches, its waves become longer and shift toward the red part of the colour spectrum. That's why it's called redshift. Think of it like this. When a car drives past you, the sound it makes is high-pitched as it comes closer, but drops to a lower pitch as it moves away. This is called the Doppler effect, and it happens with light too. When a star or galaxy moves away from us, its light stretches and its colour shifts toward red. In space, redshift shows that galaxies are moving away from us, and very fast. The farther away a galaxy is, the faster it is moving. That's why redshift is so important. By measuring how much a galaxy's light has redshifted, scientists can figure out how fast it is moving and how far it is from Earth. This discovery changed everything we knew about the universe. In the early 20th century, in the year 1929, an American astronomer named Edwin Hubble made an important observation. While looking at distant galaxies through his telescope, he noticed something amazing. Every galaxy he studied seemed to be moving away from Earth, and the farther the galaxy, the faster it moved. From this, Hubble developed what is now called Hubble's law, which says the universe is expanding. This means space itself is stretching. The galaxies aren't moving through space, they're being carried apart as space grows. This was one of the biggest clues supporting the Big Bang theory. The idea that the entire universe began from one extremely hot and dense point about 13,800,000,000 years ago. Since then, the universe has been growing, and redshift is one way we can track that growth. When scientists detect redshifted light from a galaxy, they can estimate how far away it is, and even more amazing, how long ago the light started travelling to us. The more redshifted the light, the longer it has been travelling. This means redshift doesn't just tell us distance, it lets us look back in time. When we observe a galaxy billions of light years away, we see it as it was billions of years ago. The light from that galaxy has taken a very long time to reach us, sometimes over 13 billion years. So, in a way, telescopes act like time machines. When we detect strong redshift, we're not just seeing distance, we're seeing how the universe looked when it was young. The galaxies with the highest redshifts, the ones farthest from us, show us what the universe looked like a few 100 million years after the Big Bang. These galaxies are very valuable because they give a rare look at the early universe. Back then, space was hotter, denser, and full of gas and dust. The first stars and galaxies were just starting to form, lighting up the universe for the first time. Studying these early galaxies is like looking back through time. Each new discovery helps us understand how the universe changed from a tiny, hot point into the huge and complex space we see today. To study these faraway galaxies and their redshifted light, astronomers use very powerful telescopes. The Hubble Space Telescope, launched in 1990, and the James Webb Space Telescope, launched in December 2021, are essential for this work. These telescopes can see extremely faint light from galaxies billions of light years away, light so dim and old that ordinary telescopes cannot detect it. When scientists study this light, they measure how much it has stretched. The more it stretches, the higher the redshift and the older the light is. This lets astronomers map the history of the universe, piece by piece, light by light. What do we see in these high redshift galaxies? Surprisingly, they look nothing like the big smooth galaxies we see today. Early galaxies were small, clumpy, and often oddly shaped. They were still forming stars and gathering gas and dust to grow. Many were colliding and merging, huge events that caused bursts of star formation and changed their shapes. Over billions of years, these galaxies grew bigger, calmer, and more organized, eventually becoming the beautiful galaxies we see today. By studying them in their youth, through the redshifted light, they teach us how galaxies grow, how stars are born, and how the universe has changed over time. One exciting thing about studying very distant galaxies is that it lets us look into the past when the first stars were born. These first stars are called population 3 stars. They formed shortly after the Big Bang when the universe was still young, made mostly of hydrogen and helium. At that time, the universe was dark and quiet, filled with these gases floating everywhere. Over millions of years, gravity pulled the gas together. Eventually, the clouds collapsed and the first stars were born. These early stars were huge, many times larger than the Sun, and burned hotter and brighter than today's stars. But they lacked heavier elements like carbon, oxygen, or nitrogen, which are needed for life. They were mostly hydrogen and helium. When these stars ended their lives, they exploded as supernovae. These explosions spread new elements into space, creating carbon, oxygen, iron, and more. Later, these elements formed new stars, planets, and eventually life, including humans. The birth and death of these first stars were some of the most important events in the universe. They were the first building blocks for everything: galaxies, solar systems, Earth, and all living things. By studying old and distant galaxies, scientists uncover the story of how the simple early universe became the complex universe we see today. One fascinating period in this early story is called the Epoch of Reionization. At that time, the universe changed a lot. Before this era, the universe was dark and cloudy, and light couldn't travel far. When the first stars shone, their light energized the surrounding gas, breaking it apart. The gas went from thick and foggy to clear. Suddenly, light could travel freely across space. This helped shape the clear, starry sky we see today. How do we know all this if we weren't there? The answer is redshift. Redshift happens to light from faraway galaxies as it travels across space. The light stretches and shifts to red because the universe is expanding. The farther the galaxy, the more stretched the light, and the older the image we see. So when astronomers look at galaxies with very high redshift, they are looking back in time. They see the galaxies as they were billions of years ago when the universe was young. This isn't like time travel in movies, it's more like reading an old message carried by light for billions of years. This light is like a time capsule. It has clues about how the universe looked when the first stars and galaxies were forming. By studying it carefully, scientists can piece together the story of how the universe changed, from empty space with gas to a universe full of stars, planets, and the potential for life. It's incredible to realize that the light we see today from faraway galaxies, whether from the Andromeda Galaxy or even galaxies billions of light years away, has been traveling across space for millions or even billions of years before it finally reaches us here on Earth. Every single particle of light, or photon, that lands in our telescopes carries with it a story from the distant past. It's like a tiny message sent across the universe, showing us a moment in time long before humans even existed. Thinking about this makes the universe feel unimaginably vast and ancient, and it reminds us just how small and fleeting our place in it truly is. One of the most fascinating areas of science today is the study of redshift in these ancient galaxies. By observing how light stretches as it travels through space, scientists can uncover secrets about the earliest moments of the universe, and the future looks even more exciting. Powerful new tools like the James Webb Space Telescope are helping us reach farther than ever before. In the coming years, we may finally understand how the very first stars and galaxies formed, how massive black holes appeared in the early universe, and, perhaps most thrilling of all, whether there could be signs of life beyond our planet. Each discovery takes us one step closer to answering some of the biggest questions we've ever asked about the cosmos. Galaxies are huge groups of stars, gas, dust, and something mysterious called dark matter. All of these things are held together by one strong force, gravity. Galaxies come in many different shapes and sizes. Some, like our Milky Way, are shaped like spirals, with long curved arms spinning around a central center, like a giant pinwheel. Others are more like smooth round balls. These are called elliptical galaxies, and they usually have older stars and look less detailed. Then there are irregular galaxies, which don't have any clear shape at all. These often got their strange look from violent crashes or close encounters with other galaxies. But galaxies aren't just floating randomly in space. They are the main building blocks of the universe. Inside these giant star cities, new stars are born, shine brightly, and eventually die in dramatic ways, like exploding in powerful blasts called supernovae. These cycles of life and death help shape the future of galaxies and make the materials needed to form new stars and planets. Galaxies also have planets, moons, comets, asteroids, and all the other things that make up our universe, including our own home, Earth. Galaxies can be very different in size. Some are small, with just a few billion stars. Others are huge, with hundreds of billions or even trillions of stars. Our galaxy, the Milky Way, is in the middle. It has about 200 billion stars. And here's the truly amazing part. Scientists think there are billions of galaxies spread across the universe that we can see with telescopes. Each one has its own story, its own journey, and its own clues about how the universe began and how it keeps changing. Every galaxy, big or small, plays a part in this cosmic story. Experts think that galaxies started forming only a few 100 million years after the Big Bang, which is the name used for the huge beginning of the universe. This event is thought to have happened about 13,800,000,000 years ago. At that time, the universe was extremely hot, dense, and full of energy. The only elements around were hydrogen and helium, which are the lightest and simplest elements. As the universe cooled down, gravity started pulling together big clouds of gas and dust. These clouds became denser and eventually collapsed, creating the first stars. Over time, these new stars began to gather together to form the first galaxies. But these early galaxies were very different from the ones we see today. They were smaller, made mostly of hot young stars, and had very few heavier elements that come from older stars. Still, these early galaxies laid the groundwork for the larger, more complex galaxies that would grow over billions of years. Since the Big Bang, the universe has been expanding, stretching out in all directions. Galaxies have slowly drifted farther apart. What's even more surprising is that this expansion is not slowing down. It's actually speeding up. Scientists don't fully understand why, but it's one of the biggest mysteries in space science today. Meanwhile, galaxies have continued to grow and change. They crash into each other, merge, and form even bigger and more detailed structures. These interactions have helped shape the large galaxy clusters and star systems we see today. Recently, a powerful new telescope has changed how we think about all this. The James Webb Space Telescope, or JWST, has made discoveries that have surprised scientists worldwide. One of the most surprising findings is very old galaxies that seem to have formed much earlier than anyone thought possible. Before, scientists believed the first galaxies formed around 400 to 500 million years after the Big Bang. That's because the universe needed time to cool down before stars could form from leftover gas. But JWST has found galaxies that may have appeared even earlier, just a few 100 million years after the universe began. Even more shocking, these galaxies look mature. They have organized shapes and show active star formation. This suggests they formed much faster than we thought. One of the most amazing discoveries by JWST was a galaxy that formed only 230 million years after the Big Bang. This is much sooner than expected. For a galaxy to form so quickly, the early universe must have been very different from what we imagined. It hints that galaxy formation may have been much faster and more efficient, or that we're missing an important piece of the puzzle. These findings are very important because they challenge what we thought we knew about galaxies and the universe. If galaxies could form this fast, it means the early universe may have had special conditions, maybe unknown types of matter, faster star-making processes, or chemical mixtures we haven't yet discovered. Scientists now need to rethink their models of the early universe. Even more interesting, these ancient galaxies are full of activity. They are filled with young stars forming very quickly. Scientists had believed that early star formation would be slow, because there weren't enough heavy elements like carbon and oxygen, which are made in the cores of dying stars and needed to form new ones. But if early galaxies are forming stars so fast, it could mean that conditions for star birth were better than we thought, or that we misunderstood how the first stars were made. Some galaxies found by JWST are much larger and more complicated than expected. And what's even more surprising, these galaxies are very old, from a time not long after the universe began. Scientists used to think that the earliest galaxies were small, rough, and undeveloped. They thought it would take billions of years for galaxies to grow large and have different types of stars. But JWST has shown a very different story. These ancient galaxies already have beautiful, detailed shapes, some even with spiral arms and clear structures. They have many kinds of stars, not just one type, showing a surprising variety. This completely challenges the older idea that early galaxies were simple and messy. It's like opening a history book and finding a chapter that shouldn't exist. These discoveries raise new questions about two big mysteries in science: dark matter and dark energy. Together, these invisible forces make up about 95% of all mass and energy in the universe. Even today, scientists don't fully understand what they are or how they work. The strange shapes and fast formation of early galaxies suggest dark matter might have played a bigger role than anyone realized. Maybe it acted like a hidden frame, pulling normal matter together faster and helping galaxies form quickly. Dark energy, thought to be driving the universe's expansion, might also have stretched space in ways we didn't expect. The more we learn, the more it feels like we're just starting to uncover the universe's secrets. These findings could completely change what we thought about the early universe. Old ideas are falling apart, and scientists will need new explanations for how massive galaxies appeared so quickly after the Big Bang. This is an exciting moment in science because it means we could discover even more in the next few years that changes how we see the universe's beginnings. Because of JWST, researchers must now look again at how galaxies form and grow. That means rethinking dark matter, how stars are born, and how the universe's structure developed when it was still very young. Evidence points to a time filled with activity, mystery, and fast changes, especially during the first few 100 million years after the Big Bang. That early period, once thought to be quiet and slow, now seems full of energy and change. These discoveries open a new level of exploration. Scientists may soon learn more about how early galaxies interacted. Were they more connected than we thought? Did they grow by merging or by using energy from nearby stars and gas? These are the questions JWST is helping to answer. Another area of interest is the role of supermassive black holes, huge objects believed to be at the center of most galaxies. These mysterious giants might have helped shape galaxies from the very beginning, acting like powerful forces that affected how fast galaxies grew and how stars formed around them. Most of the galaxies we see in the sky today fall into two main groups: spiral galaxies and elliptical galaxies. Spiral galaxies, like our own Milky Way, have long, curved arms that spin outward from a bright center. These arms are made up of stars, gas, and dust, all swirling around like dancers in a cosmic whirlpool. The whole galaxy moves in a smooth, organized way. Elliptical galaxies, on the other hand, don't have arms or patterns. Instead, they look more like giant glowing balls or stretched out footballs. The stars inside them don't move in neat circles but travel in many different directions, like people walking through a crowd. These galaxies tend to be older and less active. But when scientists look far into space, so far that they are actually looking back in time, they find something very different. The oldest galaxies, formed when the universe was still very young, do not look organized at all. They are messy, bumpy, and strange. They seem to be in the middle of forming rather than already shaped. This big difference in how they look comes from how galaxies form and change over time. In the early universe, just a few 100 million years after the Big Bang, galaxies were much smaller and didn't have the neat structure we're used to. Instead of smooth spirals or clean elliptical shapes, these early galaxies looked more like cosmic puzzles with missing pieces. They were full of stars, gas, and dust clumped together in uneven patches. It's as if these galaxies were caught in the act of being built, with pieces still flying into place. This messy look shows how wild and chaotic the young universe was. Back then, galaxies were constantly bumping into each other, merging, breaking apart, and forming new shapes. The universe was a busy, noisy workshop, not a quiet museum of well-arranged galaxies. For a long time, scientists believed that galaxies would slowly grow more organized as they got older. They expected to find neat, smooth shapes even in the earliest galaxies. But when astronomers began observing the farthest galaxies, the ones that formed more than 13 billion years ago, they saw something surprising. These ancient galaxies didn't look calm or neat at all. Instead, they looked like tangled balls of stars and gas. Some were oddly shaped, with uneven lumps and jagged edges. Others looked like they were made of smaller galaxies that hadn't finished joining together yet. So how do we even know what these ancient galaxies looked like, if they are so far away, and the light from them has travelled for billions of years? The answer comes from a fascinating trick of nature: how light travels through space. Light doesn't move instantly, it takes time to reach us. The farther away something is, the longer its light takes to get here. So when we look at a galaxy that is, say, 10 billion light years away, we are not seeing it as it looks now. We are seeing it as it looked 10 billion years ago. It's like looking into a cosmic time machine. If we see a galaxy that is 1 billion light years away, then the light we are seeing left that galaxy 1 billion years ago, and we are witnessing what it looked like back then. To look this far back in time, scientists use very powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. These amazing tools can capture the faint light from galaxies that are billions of light years away. They let us see what the universe looked like when it was still young and just starting to form its first stars and galaxies. One of the most powerful tools for studying early galaxies is the James Webb Space Telescope, often called JWST. It was specially made to look deep into space and far back in time. It can see infrared light, which is important because the light from distant galaxies gets stretched into longer, redder waves as it travels across the expanding universe. JWST can pick up this ancient light, giving scientists clear views of galaxies as they looked more than 13 billion years ago. What JWST has shown us is surprising. Many of these early galaxies look much more irregular and messy than scientists expected. This discovery has challenged old ideas about how galaxies form. Instead of slowly turning into neat, organized systems, it seems that many galaxies were born messy and stayed that way for a long time. But why were these early galaxies so messy and wild? One possible answer involves something mysterious and invisible: dark matter. Dark matter is a strange type of matter that does not give off light or energy, so we can't see it with our eyes or telescopes, yet it makes up about 27% of everything in the universe. Scientists know it exists because it has a strong pull called gravity. It pulls on the things we can see, like stars, galaxies, and even groups of galaxies. In the early universe, dark matter wasn't spread out evenly. It formed dense clumps in different places. These clumps acted like giant magnets, pulling in gas and dust from their surroundings. This material then began to collapse under its own weight, forming new stars and over time entire galaxies. But because dark matter was clumped in random ways, the galaxies that formed around it didn't look smooth or regular. They were twisted and jumbled, still being shaped by the gravity of the dark matter. This may be why the earliest galaxies appear so strange. They were still under construction, shaped by invisible forces. Another reason early galaxies looked so unusual is that they were packed much closer together than galaxies are today. Back then, the universe was smaller and more crowded. Tiny galaxies floated near one another, and many of them crashed into each other. When galaxies collide, their stars usually don't hit each other. There is just too much space between stars. But the gas and dust inside the galaxies do crash, mix, and heat up. These cosmic crashes caused huge changes. The swirling clouds of gas and dust would get squeezed and heated, sparking the birth of new stars. Galaxies would get pulled into new shapes. Some would merge completely into bigger galaxies. Others would stretch, twist, or break apart. These violent events helped shape the galaxies into what we see today. Over time, this rough and chaotic dance gave rise to larger and more stable galaxies. But it all began in a time of cosmic turmoil, when the universe was still young, galaxies were still forming, and everything was changing quickly. Even now, galaxies still collide and change, but it happens less often than it did in the early days. Back then, it was a normal part of the universe's wild and dramatic story of growth. Long ago, when the universe was still very young, only a few 100 million years after the Big Bang, galaxies looked and acted very differently from the ones we see today. Back then, the early galaxies were filled with huge amounts of gas, far more than the galaxies we see now. This gas was mostly made of hydrogen and helium, the two lightest and simplest elements in the universe. These gases were the main ingredients for making new stars. Because there was so much gas flying around, early galaxies didn't have the neat and graceful shapes we often admire now, like spirals or smooth ellipses. Instead, they were wild and messy. The gas inside them was spread out unevenly, making the galaxies look lopsided, bumpy and irregular. These young galaxies were like cosmic storms, turbulent, full of motion, and still trying to find their shape. Even the way stars were born in those early times was very different. In today's galaxies, like our own Milky Way, new stars usually form in special places such as the spiral arms. These regions are organized and fairly calm, but in the early universe, star-making was much more chaotic. Stars could appear almost anywhere inside a galaxy. Sometimes they were born in giant bursts, triggered by turbulence or by galaxies crashing into each other. This scattered and uncontrolled pattern of star formation gave early galaxies their bumpy and jumbled look. All of this happened because those galaxies were still growing up. Over billions of years, galaxies collided, merged, and matured. As this happened, they slowly began to form more organized shapes. Some turned into spiral galaxies with beautiful, sweeping arms, while others became smooth and round, forming elliptical galaxies. By studying those early, messy galaxies, astronomers can learn a lot about how galaxies grow and how the universe itself has changed over time. Deep in the center of almost every big galaxy, including our Milky Way, there is something truly amazing: a supermassive black hole. These are incredibly dense objects with gravity so strong that nothing, not even light, can escape if it gets too close. But black holes aren't just sitting quietly at the center of galaxies. They can actually shape the galaxies around them in powerful and surprising ways. Scientists think that even in the earliest days of the universe, more than 13 billion years ago, supermassive black holes were already starting to form in the hearts of young galaxies. Their strong gravity could pull in huge amounts of gas, dust, and even entire stars. This strong pull didn't just affect the black hole's immediate area, it could stir up the whole galaxy, making it even more chaotic. Stars might have been thrown into strange paths, and the entire galaxy could have become unstable. But black holes don't only pull things in. Sometimes they release huge amounts of energy. As gas and dust spiral into a black hole, they heat up to extreme temperatures, creating enormous bursts of radiation. Some black holes even shoot out blazing streams of particles that travel nearly as fast as light. These bursts could push through the space around them, moving gas and dust away and even stopping new stars from forming. In this way, black holes may have played a big role in shaping the strange and uneven shapes of early galaxies. Even now, scientists are still trying to fully understand how these cosmic giants influenced the early universe. But one thing is clear: supermassive black holes were not just silent watchers. They were active, powerful forces that helped build the galaxies we see today. In the beginning, not long after the Big Bang, the universe was wild and untamed. Swirling clouds of gas, dust, and newborn stars filled space, and galaxies looked nothing like they do today. Most of them didn't have smooth shapes or neat spiral arms. Instead, they looked like scattered clumps of stars and gas, without much order at all. But over time, over billions and billions of years, something amazing happened. The invisible force of gravity began to pull everything together. Galaxies started to interact with each other, and sometimes they even crashed into one another. When two galaxies merged, their stars didn't usually collide because the space between them is so huge. But their gas and dust did interact, creating massive bursts of new stars. These galaxy collisions, although violent and dramatic, actually helped galaxies settle down. The rough and messy shapes began to smooth out. Slowly, galaxies started to look more familiar. Some formed beautiful spiral arms like the Milky Way, while others became smooth and rounded like elliptical galaxies. Even today, this process isn't finished. The universe is still changing. Galaxies continue to grow, merge, and reshape themselves. Our own Milky Way galaxy, for example, is moving toward a collision with the nearby Andromeda galaxy. This cosmic crash will happen in about 4 billion years. Eventually, the two will join into one giant galaxy. This shows that the story of galaxy growth is still unfolding. Recent discoveries have surprised scientists by showing that early galaxies were even more chaotic than anyone had expected. These new findings are changing the way we understand galaxy formation. For a long time, scientists thought that galaxies slowly and steadily took shape over time, but now we know the truth is much messier. The early universe was full of unpredictable and oddly shaped galaxies. Many of them looked like blobs or scattered groups of stars rather than anything structured. The forces that shape these galaxies are still not fully understood. The conditions back then were so different from today that researchers are still trying to figure out what exactly happened. Why were these galaxies so disorderly? What caused such wild bursts of star formation? These are questions scientists are still working hard to answer. These strange early galaxies are like the universe's first building blocks. By studying them closely, scientists can trace the history of how galaxies grow, change, and evolve over time. Each clumpy, chaotic galaxy gives us a clue about how the universe went from a wild, swirling cloud of gas to the vast, structured cosmos we live in today. For thousands of years, humans have looked up at the night sky with wonder, curiosity, and many questions. They stared at the stars and asked themselves, is Earth the only place in this huge universe where life exists? The twinkling lights in the sky have always sparked the imagination, filling people's minds with dreams of other worlds. With billions and billions of stars scattered across the endless space, many began to believe that at least some of these stars might have planets like Earth, places where life could also exist. For most of human history, though, this was just a dream. People imagined other Earths, but there was no proof. Scientists, stargazers, and dreamers kept searching and hoping, but they had no way to truly see what was out there. That all began to change in the last few decades of the 20th century. Thanks to strong new telescopes and brave space missions, scientists have now found thousands of planets that orbit stars far beyond our own sun. These planets are called exoplanets, and finding them has completely changed how we see the universe and our place in it. Some of these exoplanets might even have the right ingredients for life. While only a small number of them seem to have Earth-like conditions, each new discovery brings us one step closer to answering one of the greatest questions ever asked. Are we alone in the universe? Exoplanets are planets that orbit stars outside our solar system. Some are rocky like Earth and might have oceans, atmospheres, or even temperatures that could support life. Others are huge gas planets, like Jupiter, or strange worlds that surprise scientists. Astronomers have found exoplanets in places and forms that are completely unexpected. Some are frozen in eternal winter, covered in thick sheets of ice. Others are blazing hot, with entire oceans made of melted rock. There are even planets where it rains liquid metal, as the extreme heat in their skies turns iron into drops that fall like fiery rain from the clouds. The very first confirmed discovery of exoplanets happened in the year 1992. These early planets were found orbiting a pulsar, a dead, collapsed star that shoots out beams of radiation like a cosmic lighthouse. These planets were very strange, and showed that worlds could form even in the most unexpected corners of space. Then, in the year 1995, astronomers found a planet named 51 Pegasi b. This was the first exoplanet discovered around a star similar to our Sun. It was a gas giant, much like Jupiter, and its discovery proved that planets orbiting stars like our own are real. That single discovery opened the doors for a whole new era of exploration. Since then, scientists have confirmed the existence of more than 5,005 exoplanets, and that number continues to grow quickly. New discoveries are being made all the time, especially with the help of advanced space telescopes like the James Webb Space Telescope. This strong telescope is not only spotting new planets, but also studying the gases in their atmospheres, looking for signs of life and unlocking the secrets of worlds far beyond our solar system. But not all exoplanets are the same. Scientists group them into different types based on size, materials, and how close they are to their stars. One of the most important groups is the gas giants. Gas giants are huge planets, much bigger than Earth. Two well-known examples in our own solar system are Jupiter and Saturn. These giants are mostly made of hydrogen and helium, two gases that are lighter than air. Because of their size and brightness, gas giants are easier to spot in space and are often among the first planets scientists find when looking at distant star systems. To understand how big they are, consider this. More than 1,300 Earths could fit inside Jupiter. These planets don't have solid ground like Earth. Instead, they are wrapped in thick clouds of gas. As you go deeper into the planet, the gas becomes heavier and hotter. In the deepest parts, the pressure is so strong that even hydrogen, which is usually a gas, turns into a strange liquid. Scientists think there might be a solid center at the very middle, but no one knows for sure because we can't send spacecraft deep enough to find out. We know a lot about gas giants like Jupiter and Saturn because they shine brightly in our sky and have been studied by telescopes and space probes for many years. These planets also give off more energy than they get from the Sun, which makes them stand out even more in space. Gas giants are not rare. In fact, most of the exoplanets discovered so far are gas giants. One big reason is that they are easier to see. When a gas giant passes in front of its star, it causes a small dimming of the star's light, something called a transit. These dips in brightness allow astronomers to notice and study the planet, even if it's located trillions of miles away. Some gas giants found outside our solar system are even more extreme than Jupiter. For example, there are hot Jupiters, which orbit their stars very closely and have extremely high temperatures. Then there are ice giants like Uranus and Neptune, which, while still mostly gas, contain more water, ammonia and methane, chemicals that make them different from Jupiter and Saturn. The discovery of so many gas giants has raised many exciting questions. How do these giant planets form? How different can they be from one another? And is it even possible for life to exist on or around one of them? Perhaps on a moon that orbits a gas giant like Jupiter's icy moon Europa. Although gas giants seem too harsh and wild to support life as we know it, studying them helps us understand the building blocks of planets, how solar systems form, and what other types of worlds might be out there in the great unknown. Each gas giant we find adds a new piece to the cosmic puzzle, bringing us closer to understanding the amazing variety of planets in space, and maybe, just maybe, bringing us closer to finding life beyond Earth. Next, let's look at the amazing Neptune-like planets, fascinating worlds that are similar in many ways to the distant planets Uranus and Neptune, which live far out in the cold parts of our solar system. These planets are often called mini-Neptunes, because like Neptune and Uranus, they are mostly made of gases rather than solid rock or metal. However, unlike the giant gas planets such as Jupiter and Saturn, mini-Neptunes are much smaller. To understand what mini-Neptunes are, it helps to look at their bigger relatives. Neptune and Uranus are famous for their thick swirling atmospheres filled with gases like hydrogen, helium, and methane. This special mix of gases gives them their blue colour and also leads to very strong winds and violent storms. They're also called ice giants because their atmospheres and inner layers have frozen substances like water, ammonia, and methane, making them not just gas worlds, but icy ones too. Mini-Neptunes, while smaller, share many of these traits. Unlike Jupiter, the biggest planet in our solar system, a huge ball of gas, mini-Neptunes are much less massive. Their smaller size means they can still have thick, fluffy atmospheres made mostly of hydrogen and helium, but they don't have the super-dense centers that big gas giants do. Because of this, their atmospheres are lighter and thinner, though still mostly gas. One of the most interesting things about mini-Neptunes is that they usually don't have a solid surface like Earth or Mars. Instead, they are made of layers of gas and ice. Some might have a rocky center deep inside, but it's hard for scientists to study these centers directly because of the thick gases that cover them. In fact, some mini-Neptunes have cloudy skies, strong winds, and stormy weather that make them look like smaller versions of Neptune or Uranus. Astronomers are very interested in these Neptune-like planets because they seem to be quite common around other stars. So far, thousands of planets have been found outside our solar system. These are called exoplanets, and many of them are mini-Neptunes. Some studies even suggest that mini-Neptunes could be one of the most common types of planets in our galaxy. What makes them even more exciting is how different each one can be. Some mini-Neptunes have thick clouds that trap heat, making them very hot inside. Others may have lighter atmospheres mixed with different ices and gases, leading to unique weather patterns and wild storms unlike anything we see on Earth. Even though they look like Neptune, these planets are different in other ways too. Because they are smaller, they might not have the strong magnetic fields or giant storms that their larger cousins do. But they can still be very active, with strange weather systems and maybe even oceans hidden deep beneath their clouds. Studying these strange worlds gives scientists important clues about how planets form and change over time. Every new discovery helps us understand more about our universe and raises new questions about what might be possible on other planets. As our technology keeps getting better, we may soon be able to take a much closer look at these mysterious worlds. Future space missions could send robotic spacecraft to explore planets like these in detail, helping us unlock their secrets and learn even more about the kinds of worlds that exist beyond our solar system. Now let's move on to another exciting group of planets, super-Earths. These are planets that are bigger than Earth but smaller than Neptune. They don't get as huge as the giant gas planets like Jupiter or Neptune, but they are still much bigger than our own planet. The term super-Earth just means how big and heavy they are. It doesn't mean they are exactly like Earth or that they can support life. Some super-Earths may have hard surfaces made of the rock, just like Earth. Others might be covered in thick layers of gas or ice. What makes them especially exciting is that some of them could have the right conditions for life. Scientists think that if a super-Earth is at just the right distance from its star, not too hot and not too cold, there might be liquid water on its surface. And since water is needed for life as we know it, these planets could possibly have living things, from tiny microbes to more complex creatures. Another interesting thing about super-Earths is their gravity. Because they are heavier than Earth, their gravity would be much stronger. If a person stood on one, they would feel much heavier and find it harder to walk or jump. But this stronger gravity could also help keep a thick atmosphere, which would protect the surface from harmful space radiation, something important for life to survive. Super-Earths come in many types. Some might be ocean worlds, with water covering the whole planet. Others could have thick clouds and hot air, more like the planet Venus. Some may be full of valuable minerals or have chemicals that don't exist on Earth. Because they are so big, super-Earths might also have very active insides, with melted rock and even volcanoes. This volcanic activity could help make and keep a stable atmosphere by releasing gases over millions of years. And if they have magnetic fields like Earth does, these planets could be protected from harmful solar winds, making them more like Earth and possibly able to support life. Astronomers have already found many super-Earths around faraway stars. Thanks to powerful new telescopes, we can now study them more closely than ever. Some well-known examples, such as Kepler 22b and TOI 700d, have made news because they seem to be in what scientists call the habitable zone. This is the perfect area around a star where the temperature is just right for liquid water to exist. In our solar system, there are 4 special planets known as terrestrial planets. These are Earth, Mars, Venus, and Mercury. What makes them different is that they are mostly made of solid rock and metal. They have strong, firm surfaces that you could actually stand on, unlike the big gas planets like Jupiter and Saturn. Those gas giants are mostly gas and don't have any solid ground under their clouds, so if you tried to land on them, you would just sink. Because of their solid surfaces, terrestrial planets are very interesting to scientists who are trying to find out if other planets could support life. These rocky worlds may hold the key to discovering life beyond Earth. Earth is the most famous of all the terrestrial planets. Why? Because it's the only one we know for sure that has life on it. People, animals, plants, bacteria, everything we know that lives is right here. That's why scientists are always excited to find other planets that might be like Earth. They want to know, could there be another planet where life exists? This curiosity makes Mars, Venus, and Mercury very interesting to space explorers. Take Mars, for example. Often called the red planet, it has a dusty, rocky surface and shows signs that long ago rivers and lakes may have flowed there. Some scientists think that billions of years ago, Mars might have had the right conditions for life. That's why space agencies like NASA have sent several robotic rovers, like Curiosity, Perseverance, and others, to drive on its surface, take pictures, dig into the soil, and look for clues that life might have once been there. Then there's Venus, which is sometimes called Earth's twin. That's because it is about the same size as Earth and made of similar materials. But don't let the nickname fool you. Venus is a very dangerous place. Its surface is extremely hot, even hotter than an oven, and it is covered in thick clouds filled with poisonous gases. Even though it is very different from Earth, scientists are still very curious about Venus. Studying it might help us understand how planets change over time and why Venus became so harsh while Earth stayed full of life. Mercury, the smallest of the terrestrial planets, is closest to the Sun. Because of that, it has some of the most extreme temperatures in the solar system. During the day, Mercury gets so hot it could melt lead. But at night, without any atmosphere to keep the heat in, it becomes colder than an icy desert. Scientists are interested in Mercury because its surface is covered with craters from space rocks, and it gives us a good chance to study what happens when a planet has no atmosphere to protect it. What all these rocky planets have in common is that they have solid ground. That makes them different from the gas giants and important for scientists looking for planets beyond our solar system, called exoplanets. Experts are especially interested in finding rocky exoplanets that are in a special part of space called the habitable zone. The habitable zone is often called the Goldilocks zone, a term from the famous fairy tale where Goldilocks liked things that were not too hot, not too cold, but just right. In space, this zone is the area around a star where a planet is at the right distance to have liquid water on its surface. Not frozen water, not steam, but liquid water, like the kind we drink, swim in, and use for farming. This is very important because all living things on Earth, tiny microbes or big animals, need liquid water to survive. If a planet is too close to its star, like Venus, it gets way too hot. Any water would quickly boil and disappear. It would be like standing next to a giant fire. You would burn. On the other hand, if a planet is too far, like Mars, it gets too cold. Any water would freeze solid, turning the planet into an icy wasteland. But Earth sits in that perfect middle spot. It is not too close and not too far from the Sun. This allows lakes, rivers, oceans and even clouds to form and stay, creating a place where life can grow. This perfect distance from the Sun is one reason Earth is so special. It allows water to move freely, and that water supports many forms of life, from fish in the sea to birds in the sky, and of course, people. But distance alone is not enough. A planet also needs a protective atmosphere. Think of a planet's atmosphere like a soft, invisible blanket wrapped around it. This blanket helps keep some of the Sun's heat and protects the planet from harmful space radiation and meteors. Without an atmosphere, a planet's temperature could swing wildly from freezing cold at night to burning hot during the day. That would make it very hard for life to survive. Earth's atmosphere is made of many different gases. One of the most important is oxygen, which we breathe in every second to stay alive. Another important gas is carbon dioxide. Even though we only need a little of it, it plays a big role. It helps keep Earth warm by trapping heat. This is called the greenhouse effect. If we didn't have enough carbon dioxide, Earth could get too cold. But if there is too much, it could become dangerously hot. So it's all about balance. Let's start by thinking about the Moon. Unlike Earth, the Moon has no atmosphere at all. This means there is no air to breathe, no clouds in the sky, and no protection from the harsh space environment. Because of this, temperatures on the Moon change wildly. When the Sun shines on the Moon during the day, it becomes very hot, over 250 degrees Fahrenheit. But when night comes, the temperature drops to a freezing -280 degrees Fahrenheit. There is nothing to hold in the heat, and nothing to block the Sun's harmful rays. Without an atmosphere, the Moon is completely exposed. It is beautiful to look at from Earth, but life could not survive there. Now let's look at Venus. Venus is very different from both the Moon and Earth. Instead of no atmosphere, it has one that is far too thick. This thick layer of gas is mostly carbon dioxide, a gas that traps heat very well. Because of this, Venus has what scientists call a runaway greenhouse effect. In simple words, this means heat keeps building up and does not escape. As a result, the surface of Venus gets unimaginably hot, around 900 degrees Fahrenheit. That is hotter than the inside of a regular kitchen oven set to its highest temperature. On top of that, the air on Venus is full of poisonous gases. With deadly heat and toxic air, Venus is one of the most dangerous places in the solar system. Nothing we know could live there. This shows how important an atmosphere is. For a planet to support life, it needs an atmosphere with the right mix of gases. The atmosphere must trap just enough heat to keep the planet warm, but not too much. It also needs to block dangerous radiation from space. If a planet has too thin an atmosphere, it will freeze. If the atmosphere is too thick, it will bake. Earth is special because it has the perfect balance. It is just right, not too hot, not too cold, and safe for life. But there's another invisible hero that protects life on Earth, our planet's magnetic field. Think of it as a giant invisible shield that surrounds the Earth. This shield protects us from harmful energy that constantly comes from the Sun. This energy is called solar radiation, and without the magnetic field it would hit Earth directly. Over time, it could even strip away our precious atmosphere, leaving us completely unprotected. Why is that so serious? Because our atmosphere does more than just hold air. It gives us the oxygen we breathe and the nitrogen that helps keep everything balanced. It also acts like a blanket, keeping Earth's temperature steady and comfortable. If solar radiation were allowed to hit Earth without any protection, it would slowly wear the atmosphere away. Without air to breathe, without protection from the sun's heat, Earth would become a lifeless, frozen world. Now, let's look at Mars. Long ago, Mars may have had a magnetic field like Earth's, but at some point, it disappeared. Once Mars lost this protective shield, the sun's radiation started attacking its atmosphere. This didn't happen quickly. It took millions of years, but eventually much of the Martian atmosphere was blown away into space. Today, Mars has only a thin layer of air, far too weak to trap heat or keep the surface safe from radiation. That's why the planet is now dry, cold, and empty. No oceans, no forests, and no signs of life. But there's something interesting about Mars. Scientists believe it may once have looked more like Earth. It might have had a thick atmosphere, flowing rivers, and even shallow seas. Some think it may have had the right conditions for life to start, but with no magnetic field to protect it, Mars couldn't keep these things. The sun stripped it bare. Today, it stands as a dusty, frozen reminder of what can happen when a planet loses its shield. This makes Earth's magnetic field even more important. It's not just a random feature, it's one of the main reasons why life is possible here. Without it, our world could have ended up just like Mars, cold, dead, and lifeless. Now let's talk about another key ingredient for life: water. Specifically, liquid water. Just being in the habitable zone isn't enough. This zone is the area around a star where a planet isn't too hot or too cold for water to exist. But even if a planet is in the right spot, it still needs water in the right form. Water in liquid form is very important. It's the perfect place for the chemical reactions that life needs to start and survive. Ice or water vapor isn't good enough. Life as we know it depends on having oceans, rivers, lakes, or even underground water flowing beneath the surface. Think about Earth. Our planet is full of life, and one big reason is because we have so much liquid water. The oceans cover most of Earth's surface. Without them, life would have a much harder time surviving. That's why, when scientists look for other worlds that might have life, the first thing they search for is signs of water. But finding water on other planets is not easy. Scientists use huge telescopes and advanced tools to look for tiny clues. They study the light from distant planets to see what kinds of gases are in their air. They look for temperatures that are not too hot or too cold, just right to keep water from freezing or boiling away. It's a tricky job, but finding liquid water gives us the best hope of discovering life beyond Earth. However, there's something else that matters for supporting life: the kind of star a planet orbits. Stars come in many sizes and temperatures, and that makes a big difference. Some stars are much bigger than our Sun. These stars are very hot and bright, but they burn through their fuel very quickly. They live fast and die young, sometimes in just a few million years. That doesn't give planets around them enough time for life to grow and evolve. The heat and radiation from these stars can also make it too hard for life to survive. On the other hand, there are smaller stars that are cooler and dimmer than the Sun. These stars live much longer, sometimes for tens of billions of years. But because they're not as hot, their planets have to be much closer to get enough warmth. If a planet is even a little too far away, it could be too cold for water to stay liquid. The best stars for life are the ones that are just right, like our Sun. Stars like the Sun are steady, warm, and live for billions of years. They shine evenly and give planets plenty of time to develop and support life. These stars offer the kind of balance that life needs. Even stars a little smaller than the Sun, called K-dwarfs, are good choices. These stars burn their fuel slowly and shine for a very long time, sometimes up to 40 or 50 billion years. That's much longer than the Sun will last, and even though they're a bit cooler, they can still give the right conditions for life on nearby planets. Exoplanets are planets that orbit stars far beyond our own solar system. These distant worlds can be millions or even billions of miles away from Earth. So far, in fact, that scientists cannot see most of them with their own eyes, not even through regular telescopes. But that doesn't stop them. Astronomers have found smart, indirect ways to discover these faraway planets. They study the light from distant stars and how it behaves. They also watch how stars move slightly. With these methods, they can uncover hidden planets that would otherwise remain invisible, giving us a peek into the vast and mysterious universe. One of the most common ways scientists detect these hidden planets is called the transit method. Think of it like this. If you shine a flashlight and a tiny bug flies in front of the beam, you'll notice a brief shadow. That's exactly what happens on a cosmic scale when a planet passes in front of its star. Here's how it works. Scientists carefully watch a distant star, which could be hundreds or even thousands of light years away from Earth. 1 light year is the distance light travels in 1 year, about 6 trillion miles. These stars shine brightly, and when a planet moves across the face of the star from our view, it blocks a small bit of the star's light. This makes the star's brightness drop slightly. The change is so small you wouldn't notice it just by looking, but special instruments can measure it. This drop in brightness happens regularly, depending on how often the planet orbits the star. The amount of light the planet blocks tells scientists about the planet's size. The bigger the planet, the more light it blocks. By watching these dimming patterns over time, astronomers can tell that something is moving in front of the star. And that something is usually a planet. This clever method doesn't just help them find planets, it also gives clues about how big the planet is, how long it takes to orbit its star, and even if the planet might be in what's called the habitable zone, the perfect distance from the star where temperatures might be just right for life to exist. A special telescope called the Kepler Space Telescope, launched by NASA in the year 2009, used this method for many years. It kept its eye on more than 150,000 stars and discovered thousands of exoplanets. Thanks to Kepler, we now know that planets are very common in our galaxy, and some might even be similar to Earth. Another amazing method scientists use is called the radial velocity method, often nicknamed the wobble method. Here's the idea. When a planet orbits a star, its gravity tugs gently on the star. It's like a small child pulling on a parent's hand. The star doesn't stand still, it moves just a little, almost like a gentle wobble. This wobble is too small for the human eye to see, but powerful instruments can detect it. These tools study the light coming from the star and notice tiny changes caused by something called the Doppler effect. You've probably noticed this effect when a car zooms by and the sound changes as it moves, higher pitched as it comes closer, lower pitched as it moves away. Light from stars does something similar. When a star moves toward us, its light shifts slightly to blue. When it moves away, the light shifts toward red. By measuring these color shifts, scientists can figure out that a planet is pulling on the star. Even if the planet is so far away that we'll never see it directly, this method lets scientists detect it. It can also tell them how heavy the planet is, how far it is from its star, and sometimes even what its orbit looks like. Over the years, this technique has helped discover hundreds, and possibly even thousands of exoplanets. It's like hearing the quiet steps of a hidden traveler walking through space. Sometimes, scientists get lucky and can take actual pictures of exoplanets. This rare and amazing method is called direct imaging. But it's not easy. Stars are extremely bright, and the planets around them are much dimmer. Trying to take a picture of a planet next to a bright star is like trying to see a tiny candle flame next to a spotlight. To fix this, astronomers use special telescopes with technology that can block the star's blinding light. This lets them focus on the much weaker light coming from the planet. It's like wearing sunglasses that help you see something small and dim next to something very bright. Direct imaging doesn't happen often, but when it does, it's a big deal. These rare images help scientists study a planet's size, color, and even its air. They can learn if the planet is rocky like Earth, icy like Neptune, or gassy like Jupiter. They can also look for signs that the planet might support life. Every time a new planet is photographed, it brings us one step closer to understanding the countless worlds that exist in the universe. Another amazing method used by scientists is called gravitational microlensing, and it sounds like something from a science fiction movie, but it's real and very powerful. Here's how it works. Gravity can bend light. So, when a huge object, like a star, moves in front of a more distant star, the gravity from the front star bends and makes the light from the one behind it look brighter. If there's a planet moving around the front star, it can make a small extra flash in the brightness. This tiny flash of light is enough to tell scientists that a planet is there. This method doesn't need any light from the planet itself. Instead, it uses gravity and light from stars far behind it. That's why gravitational microlensing is very useful for finding planets that are too far away or too dim for any other method. Even though it's rare and hard to predict, this method can find planets that no other method can. Some of the most distant and unusual exoplanets we've found were discovered this way. Imagine a lonely planet floating through the endless darkness of space. Far away, a distant star shines, sending out its light across billions of miles. Usually the star's light travels straight toward us here on Earth. But sometimes something special happens. If that wandering planet passes directly in front of the star, it creates a surprising and powerful effect. Instead of just blocking the light, the planet's gravity bends it, like a magnifying glass bending sunlight. This bending makes the distant star look brighter, and sometimes even larger than it really is. This strange effect happens because gravity isn't just a force, it also changes the shape of space around it. This idea comes from Albert Einstein's famous theory of relativity. The heavier something is, like a planet, a star, or a black hole, the more it pulls and twists the space around it. So, when a planet passes directly between us and a faraway star, its gravity slightly bends the light coming from the star. This bending creates a short brightening that we can see from Earth. Scientists call this amazing event gravitational microlensing. It doesn't last long, but it can show us something we would never have seen otherwise. What makes gravitational microlensing so amazing is that it can find planets we can't see any other way. Most planets are discovered by either watching how their light shines, or by noticing how they gently pull on their parent stars with their gravity. But these normal methods don't always work, especially if the planet is very small or very far from its star. Microlensing gives us a rare look at these hidden worlds, even if they're light years away. It's like finding a hidden gem in the night sky. When that short brightening happens, scientists on Earth quickly use strong instruments to measure how much the star's light changes. From that tiny flash, they can figure out amazing details: how big the planet is, where it is, and how far it orbits from its star. But gravitational microlensing doesn't just help us find planets. It also helps discover other mysterious things in space, like black holes, neutron stars, or strange objects we still don't fully understand. Since many planets found using this method are far away in the galaxy or even the universe, this method opens up a whole new way of exploring space. It lets astronomers reach farther than ever before, into places they once only dreamed of studying. Thanks to this and other advanced methods, astronomers have already found many fascinating exoplanets, planets that orbit stars outside our solar system. Some of these planets are especially exciting because they might have the right conditions for life. Here are a few of the most promising examples. Proxima b. This planet orbits a star called Proxima Centauri, the closest star to our solar system. It is just over 4 light years away. Proxima b is in what scientists call the habitable zone, the area around a star where the temperature might be just right for liquid water. Water is important because it is needed for life as we know it, but scientists are still trying to find out if Proxima b has a strong enough atmosphere to protect it and make it livable. The TRAPPIST-1 system, about 40 light-years from Earth, is a special star system called TRAPPIST-1. This system has 7 planets that are all about the same size as Earth. Even more exciting, 3 of these planets are in the habitable zone. If these planets have the right conditions, like water and an atmosphere, they might support life. That's why TRAPPIST-1 is one of the most watched systems in the universe. Kepler 442 IB. This planet, often called a super-Earth, is about 1,200 light-years from Earth. It is bigger than our planet, but it orbits in the habitable zone of its star. Scientists think it might have the right temperature, and maybe an atmosphere that could support life. That makes Kepler 442b one of the most interesting candidates for life. LHS 1140b. This rocky world is about 40 light-years away from Earth. Astronomers are interested in it because it is thought to have a thick atmosphere and may even have liquid water on its surface. Its rocky land is similar to Earth's, making it another strong possibility in the search for alien life. Discovering the universe's very first stars is like peeking through a magical window into a time long, long ago, so far back that it feels almost impossible to imagine. These ancient stars, called Population 3 stars, are completely different from the stars we see in the sky tonight. What makes them truly extraordinary is that they were made from just two simple ingredients, hydrogen and helium. Right after the universe was born in an enormous explosion called the Big Bang, these were the only elements floating through space. There were no heavier elements yet, nothing like carbon, oxygen, or iron existed at that time. These very first stars didn't appear instantly. They formed during the universe's early, wild, and mysterious years, long before galaxies, planets, or anything like our solar system existed. Today, scientists are using the James Webb Space Telescope, often called JWST, to search for clues about these ancient stars. This remarkable telescope acts like a cosmic time machine, letting us look back billions of years to see what happened near the very beginning of everything. To understand how these stars came to exist, we have to go back about 13,800,000,000 years to the moment of the Big Bang. That was the instant when the universe began, an unimaginably hot and dense explosion that set everything in motion. In the first few minutes after this event, only the simplest elements could form: hydrogen, helium, and tiny amounts of lithium. Hydrogen, the lightest and most common element in the universe, is made of just one proton. Helium, a little heavier, has 2 protons and 2 neutrons. Together, these simple elements became the building blocks of everything that followed. Heavier elements like carbon, oxygen, and iron would only appear later, created deep inside the cores of stars. In the beginning, the universe was dark and quiet. There were no stars, no galaxies, no light, only huge clouds of invisible gas drifting through empty space. This long period of darkness is known as the Cosmic Dark Ages, and it lasted for hundreds of millions of years. It was a time of stillness, but beneath the calm, a powerful force was slowly at work. Gravity, the invisible pull that draws things together, began gathering the hydrogen and helium gas into clouds. Over time, these clouds grew denser and hotter as gravity squeezed them tighter. Eventually, the first stars ignited, shining for the very first time and lighting up the universe. These population 3 stars were nothing like the ones we see now. They were enormous, hundreds or even thousands of times bigger than our Sun. Because they were so massive, they burned their fuel incredibly fast, living short but brilliant lives. While our Sun can shine for billions of years, these giant stars lasted only a few million years before exploding in spectacular blasts. Since they were made only of hydrogen and helium, they lacked the heavier elements that modern stars have. That is why scientists gave them the special name Population 3, distinguishing them from younger stars which are called Population 2 and Population 1. Population 3 stars did something astonishing. They ended the darkness of the Cosmic Dark Ages. Their light, especially in the form of ultraviolet radiation, transformed the universe in a process called cosmic reionization. Before this, neutral hydrogen gas filled space and blocked light from travelling far. The ultraviolet radiation from these stars had enough energy to strip electrons from hydrogen atoms, turning the gas into ionized hydrogen and making space transparent. For the first time, light could move freely across the cosmos. This was a turning point in the history of everything. Even though these stars lived short lives, their deaths were dramatic and world-changing. They exploded as supernovae, massive cosmic blasts that spread newly made elements across space. These explosions created carbon, oxygen, iron, and even gold, which would later become part of new stars, planets, and eventually life itself. In this way, the deaths of Population 3 stars were not just endings, they were also the beginnings of everything that followed: solar systems, oceans, forests, animals, and humans. Studying these stars is extremely challenging because they are so far away. The light from them has been travelling through space for more than 13 billion years, and by the time it reaches Earth, it is faint and difficult to detect. Scientists don't usually see the stars directly. Instead, they look for clues left behind, like enormous bubbles of ionized hydrogen created by the star's powerful light. Measuring these bubbles helps astronomers understand more about these ancient giants. Learning about Population 3 stars is not just about the distant past, it also helps us understand how life began. These stars were the first to create the heavy elements necessary for planets and living beings. By studying how these stars lived and died, scientists can trace the story of our own planet and life on it. Population 3 stars also played a key role in shaping the universe. They helped form galaxies, black holes, and other massive structures. Following the story of these stars from their birth in dark clouds to their fiery deaths lets us piece together the grand puzzle of how the universe evolved over time. Each new discovery adds another piece to this cosmic puzzle, helping us see the bigger picture of how everything in space, including ourselves, came to exist. Thanks to the amazing power of the James Webb Space Telescope, scientists are now closer than ever to unlocking the secrets of the first stars. JWST is already showing us incredible glimpses of the early universe and promises to reveal even more, including how the very first galaxies were born. A biosignature, sometimes called a chemical fossil or a molecular fossil, is any kind of substance or pattern that could be a sign that life exists or used to exist on a planet. This evidence might come from an element, a special kind of molecule, or even a strange pattern in the atmosphere. These clues don't have to be living things themselves. They can be leftovers or byproducts of life, like a fingerprint left behind after something was there. Scientists who study astrobiology, the study of life in the universe, use biosignatures to help them look for signs of life beyond Earth. These signs can appear in many different forms. For example, some gases or unusual chemical mixes in a planet's air might suggest that living things are there. In other cases, scientists might find strange rock shapes, tiny fossils, or changes in a planet's light that could all be hints of alien life, whether it's tiny microbes or even advanced civilizations. Biosignatures are divided into 10 main types, each giving a different kind of evidence that life might be, or once was, there. Isotope patterns. Living things use elements like carbon or oxygen in very specific ways. When they do, they leave behind isotope patterns, versions of elements with different weights that are very different from patterns made by non-living processes. Chemical signatures. Some chemicals, like oxygen and methane, can only exist together if something keeps making them. That something could be life. Organic matter. Life forms naturally make organic molecules like proteins, fats, and sugars. These can sometimes get trapped in rocks or mud and stay there for millions, or even billions of years. Biological minerals. Some tiny life forms make minerals in ways that nature alone does not. For example, some bacteria create special crystals of magnetite which are different from the ones made by volcanoes or other natural forces, microscopic structures. Under a microscope, scientists might see tiny patterns or textures, like microfossils or thin films of bacteria, that suggest living things were once present. Macroscopic structures. On a larger scale, scientists may find big rock formations like ancient coral reefs or layered rocks called stromatolites that were built by colonies of microbes long ago. Changes over time. If a planet's atmosphere or surface light changes regularly, like in cycles, it might mean life is affecting it, just like Earth's plants change our oxygen levels. Surface reflectance features. Some life forms have pigments, color molecules, that change how a surface reflects light. These changes can sometimes be seen from space. Atmospheric gases. Gases like oxygen, methane, and nitrous oxide often come from living organisms. If we find them in the air of another planet, it might mean something alive is there. Technosignatures. These are signs of intelligent life, such as artificial lights, radio signals, or pollution, things that could not happen naturally. Not every strange pattern or odd chemical mix is a sure sign of life. To be trusted, a biosignature has to follow 3 main rules. Reliability. It must be something usually made by life and not easily explained by non-living processes. Survivability. It must last long enough so we can find it. Detectability. We need the tools and technology to actually notice and measure it. One big problem is that nature, without life, can sometimes copy the effects of life. For example, volcanoes or chemical reactions in rocks can sometimes release gases like methane or oxygen, making scientists think life might be there. So researchers must be very careful and check every other possible explanation before making conclusions. One smart way scientists handle this is by looking for chemical imbalances that don't make sense unless something, possibly life, is keeping them going. For example, if a planet's air has both oxygen and methane at the same time, that's a strong clue. Normally, those 2 gases would react with each other and disappear quickly. If both are still present, something must be producing more of them, possibly some form of life. For a biosignature to be useful, it has to last long enough for our tools, like space probes, telescopes, or even astronauts, to find it. One way this happens is through waste left behind when living things use energy. These metabolic byproducts are like footprints of life, showing where it has been. Also, the physical remains of life, such as fossils, can be preserved for a very long time. In fact, scientists have found fossils on Earth that are as old as 3.5 billion years. These preserved signs are some of our best evidence that life existed long ago. However, even if life leaves behind signs, we still need the right tools to find them. Sometimes our telescopes or instruments aren't strong enough to detect the tiny changes or signals. Life might exist, but we might miss it simply because our technology isn't advanced enough yet. Some biosignatures are easier to spot than others. For example, oxygen is one of the most promising. On Earth, it's mostly made by plants and microbes during photosynthesis, the process of turning sunlight into energy. It's also needed for many animals to breathe. Oxygen leaves a clear signal in a planet's atmosphere and is easy to detect because it changes how light passes through the air. But there's a catch. Oxygen can also form without life. A process called photolysis, where light breaks apart water or carbon dioxide, can produce oxygen. If a planet loses its water or lacks other gases, oxygen might build up naturally. That's why scientists must be very careful not to mistake a natural process for a sign of life. They need creativity, careful study, and deep knowledge to tell the difference between living and non-living causes. There's also the opposite problem: false negatives. This is when life really exists, but its signs are too weak or hidden for us to see. Maybe the atmosphere hides the signals, or maybe life exists deep underground where we cannot detect it. Scientists are studying this problem carefully, especially as they prepare for the next generation of telescopes that will look at the skies of distant planets. Finding biosignatures isn't just about what's out there, it's also about the tools we use on Earth. One issue is telescope clarity. If a telescope isn't sharp enough, it might miss subtle signs of life. Also, many telescopes and space missions are designed by large teams of scientists with different goals. Sometimes they have to make trade-offs, like choosing to study a planet's weather instead of focusing only on life. This means some biosignatures might be harder to find simply because the mission wasn't built to look for them. Earth's own history gives us a useful guide. Our planet has had life for billions of years, and much of that life has left behind chemical clues. Fields like geochemistry, geobiology, and geomicrobiology study these old traces, helping us understand what biosignatures really look like. Some important examples include microfossils and stromatolites, structures built by ancient microbes, sometimes layered in beautiful patterns. Molecular markers, or biomarkers, specific molecules made only by life, like certain fatty acids and alcohols. Isotopic patterns, life tends to use elements like carbon, nitrogen, and hydrogen in ways that leave unusual isotope ratios. Metal patterns, some metals like iron, molybdenum, chromium, and rare earth elements change their amount or type in the presence of life and environmental changes. For example, by analysing types of fatty acids in a rock, scientists can figure out which kinds of bacteria or archaea once lived there. Long-chain fatty alcohols, especially those with more than 23 carbon atoms, are signs of planktonic bacteria. Other molecules like alkanes, alcohols, and fatty acids with 20 to 36 carbon atoms often come from higher plants. These are usually found in soils and ancient peat deposits formed from plant waxes. Life has a way of leaving special clues that can show it was once present, even if that life disappeared millions or billions of years ago. These clues are called biosignatures, and they can take many forms. Some biosignatures are chemical, like tiny bits of special molecules including DNA, fats, proteins, and amino acids, the building blocks of life. Others are strange substances that look like kerogen, a type of fossilized organic matter. Biosignatures can also appear as unusual patterns or shapes in rocks and sediments that hint at something that was once alive. Tiny life forms, like microbes, are especially good at changing the environment around them. As they live and grow, they create chemical changes and leave marks in the materials they touch. For example, some types of bacteria can make tiny holes in carbonate rocks. Under a microscope, these holes look like little swirls or branches. They are very different from the natural bubbles or spaces in ordinary rocks. These special patterns can be strong hints that microbes were once there. But it's important to be careful, because just finding a strange shape doesn't automatically mean life made it. Sometimes, nature itself can make patterns that look like life, even when no living thing is involved. One of the most famous examples of this mystery comes from a Martian meteorite named ALH 84001. This space rock was found in Antarctica and is thought to have come from Mars. Inside it, scientists found tiny crystals of a mineral called magnetite, along with tiny shapes that looked a lot like bacteria. At first, many experts were excited. They thought this might really be evidence of ancient life on Mars. But as time went on and more studies were done, most scientists started to believe that the shapes were just too small to be real fossilized cells. The debate continues, even after more than 25 years, making it one of the longest-running scientific arguments about life beyond Earth. From this case, scientists learned something very important: morphology, which means the shape or structure of something, can't be used alone as proof of life. Even if something looks like it was made by a living thing, that doesn't mean it really was. People might see shapes in different ways, and that can lead to mistakes. Today, scientists agree that to make a strong case for life, you need more than just shapes. You also need chemical evidence and other clues. No single chemical or compound can tell us for sure that life once existed. Instead, scientists look for special patterns in organic, carbon-based molecules, patterns that only life is known to make. For example, when living cells die and break down, they leave behind lipids, or fatty molecules, from their cell membranes. These lipids often show a clear pattern. They're usually concentrated, have a certain size, and often have even numbers of carbon atoms, which usually doesn't happen in non-living chemistry. Also, living things only use left-handed amino acids, while random chemistry would make a mix of left and right-handed ones. This kind of handedness could be another strong clue. But signs of life aren't always about chemistry. They can also show up as magnetic signals. Some types of bacteria leave behind tiny magnetic particles, which can be detected long after the microbes themselves are gone. Chemical signs of life are usually made of complex molecules built from carbon, hydrogen, and other elements like oxygen, nitrogen, and sulfur. These molecules are sometimes found in things like crude oil, where they have slowly changed over millions of years from ancient living material. Each sign of life has its own unique fingerprint. This slow change of living matter into oil leaves behind a trail of proof. Many of the molecules found in oil are very large, which helps scientists spot them. Some well-known examples are pristane, steranes, and triterpenes. These chemicals come from plants, especially land-based flowering plants, and are formed as the original biological material breaks down over time. When scientists study oil or the rocks it comes from, they look for tiny amounts of these signs using powerful tools like gas chromatography and mass spectrometry. These tools help them identify and measure the different molecules present. By doing this, they can figure out where the oil came from, how old it is, and what kind of environment it formed in. This is why signs of life in oil are often called chemical fossils. They record the ancient history of life, locked inside molecules. These chemical clues help geologists and chemists track the journey of oil through underground layers. The exact pattern of signs in a sample can show how far the oil has moved or if it has been mixed with something else. Because these molecules are very tough and resistant to heat, pressure, and time, they're also useful in other areas, like tracking oil spills or studying polluted lubricants. Still, scientists have to be careful when examining raw rock samples, since these can be contaminated or broken down by natural processes over the years, making it harder to get accurate results. Now, when it comes to finding life on other planets, scientists often look at atmospheres, since they can hold important clues. Over time, life changes a planet's atmosphere in ways that natural processes cannot. Earth, for example, has huge amounts of oxygen and small amounts of methane in its air, both gases that come from living things. This unusual mix is hard to explain without life. Even the colour of a planet might hint at the presence of life. Life that uses sunlight for energy, like plants, often contains special pigments, which reflect light in unique ways. By looking at how a planet reflects light, scientists can guess whether it might have plants or something similar. This method is called studying the planet's reflectance spectrum. Some life forms can even glow under ultraviolet light, which could be seen by powerful telescopes from space. Recently, scientists have started finding gases like hydrogen and methane in the skies of distant planets. But just seeing these gases isn't enough. We also have to understand how the planet's atmosphere behaves. For example, finding both oxygen and methane on the same planet could be a very strong sign of life. That's because these two gases usually react and cancel each other out, so if they both exist at the same time, something must be constantly making them, most likely something alive. Other interesting gases to look for include dimethyl sulfide and chloromethane, as well as combinations like methane and carbon dioxide. One of the most exciting recent discoveries is the possible presence of phosphine in the atmosphere of Venus. On Earth, phosphine is mostly made by living organisms, so its presence on another planet could point to life, though more research is still needed. When a planet's atmosphere is out of balance, it can be a signal that life is doing something unusual. Earth's atmosphere, for example, has been shaped and changed by life in ways that would never happen through natural chemistry alone. Since Earth is the only place we know for sure has life, scientists often use it as a model. But they also know that alien life might be very different. It might not use the same chemicals or leave the same kinds of signs we see here. That's why some researchers look for what they call agnostic biosignatures, signs of life that don't depend on Earth-like biology. They believe that all life, no matter how strange, needs energy to survive. And to get energy, there must be some kind of chemical imbalance, a condition that living things can use. By understanding the balance created by non-living processes, scientists can spot when something is off, which might mean life is present, even if it's nothing like what we've seen before. Finding signs of life on another planet, like a biosignature, is one of the most exciting discoveries scientists can make. A biosignature is something that hints that life, either in the past or present, may exist somewhere beyond Earth. But interestingly, discovering that a planet does not have life can also be just as important. Life depends on special kinds of chemical conditions, especially something known as redox imbalances. This happens when certain chemicals are more likely to either gain or lose electrons, creating energy that living things can use. Now, if a planet has this kind of energy-rich environment, but there's no life to use it, that's called an anti-biosignature. It's like seeing a dinner table full of food but no one sitting down to eat. It tells us something valuable about the place. It could mean that life never existed there, or that something happened to wipe it out. One interesting idea about life is the polyelectrolyte theory of genes. This idea says that for a molecule like DNA, or any similar genetic material, to evolve naturally, it needs to have a special repeating structure. In the year 2002, two scientists named Stephen A. Benner and Daniel Hutter suggested that DNA, or any life-forming molecule, must be a polyelectrolyte. That means it has repeating charge sections that help it work properly in water. Without this structure, the molecule wouldn't be able to evolve. These scientists even suggested ways to look for such genetic materials on places like Mars, Enceladus, one of Saturn's moons, and Europa, one of Jupiter's moons. One of the most debated questions in the search for life on Mars involves a simple gas, methane. Methane is important because it breaks down quickly in a planet's atmosphere when exposed to sunlight and other natural processes. So, if there's more methane than expected, it could mean that something, possibly life, is constantly making it. Since the year 2004, different spacecraft and telescopes on Earth have reported finding methane in the thin atmosphere of Mars. The amounts found have changed a lot, from as little as 0.24 to 0.65 parts per billion, and in some rare spots, even as high as 45 parts per billion. These are very tiny amounts, but they still matter. However, more recent data from a very advanced instrument on board the ExoMars Trace Gas Orbiter, launched in 2016, told a different story. This spacecraft didn't detect any methane at all, and it set a new upper limit of only 0.05 parts per billion. That's incredibly low, so low that it seems to contradict the earlier findings. This strange difference has made the mystery of Martian methane even more puzzling. Even more confusing is how fast the methane seems to appear and disappear. Right now, scientists don't fully understand how chemicals behave in Mars' atmosphere. The way methane comes and goes so quickly doesn't match any current model of how gases are supposed to break down. To really solve this mystery, scientists would need to send a lander or robot with a tool called a mass spectrometer. This tool could study the kinds of carbon atoms in the methane, especially carbon-12 and carbon-14. By comparing the amounts of these carbon types, scientists could figure out if the methane came from living organisms, just like they do here on Earth. There's another piece of the puzzle too. Mars's atmosphere has a lot of carbon monoxide and hydrogen, two gases that hold a lot of usable energy. On Earth, microbes and other life forms would quickly use these gases as fuel, but on Mars they seem to just stay in the air, unused. This is another possible anti-biosignature, because it suggests that no life is there to use the available energy. To some scientists, this could be a hint that life is either not there or has not been found yet. The science that studies life in space is called astrobiology. At its core is the idea that if life exists beyond Earth, we might be able to notice it through the clues it leaves behind, like biosignatures. But for a biosignature to really count as proof of life, it must be something that living things are likely to make, and something that natural non-living processes, called abiotic processes, are very unlikely to create. To be sure a biosignature really comes from life, scientists have to rule out every other possible explanation. Like all major discoveries, finding real proof of alien life will take time, many experiments, and careful study. Back in the 1970s, NASA made history with its Viking missions to Mars, which were the first to do experiments to look for signs of life on another planet. The two Viking landers each had 3 different experiments to test whether life, especially microbial life, might exist. They looked for things like metabolism, but the results were unclear. Some tests gave hints of something interesting, but others did not, leaving scientists with no final answer. Today, NASA's Curiosity rover is still hard at work on the Martian surface. It is part of the Mars Science Laboratory mission, and its job is to explore whether Mars could have supported life in the past, or maybe still can. Curiosity has many tools that can search for signs of life, such as organic molecules, possible microbial remains, ancient chemical patterns, and special gases that might have been made by living things. It focuses on areas where organic matter might be kept safe in rocks, which increases the chances of finding ancient fossilized life. At the same time, the ExoMars Trace Gas Orbiter, launched in 2016, continues to study Mars from above. It is mapping where gases like methane come from, and this information helps scientists decide where to land future missions. One of those missions is the Rosalind Franklin rover, named after the famous scientist who helped discover DNA's structure. This rover was planned to launch in 2022, and it can drill as deep as 2 meters below Mars's surface. That's important, because under the surface, any signs of life could be better protected from the harsh radiation that hits the planet every day. Another mission, called the Mars 2020 rover, also known as Perseverance, launched in 2020. Its goal is to study parts of Mars that may once have had the right conditions for life. It is exploring the rocks, soil, and ancient environments of the planet to learn more about its history and whether it could support life. Perseverance is also collecting rock and soil samples that could one day be brought back to Earth, where scientists can study them with even more powerful tools than those sent to space. Looking beyond Mars in our search for life, one exciting mission is NASA's Dragonfly mission. This mission is planned to launch in 2025, and it will go to Titan, the largest moon of Saturn. Titan is fascinating because it has a thick atmosphere full of complex carbon-based chemicals. Scientists think Titan may have the right conditions for early forms of life, or for prebiotic chemistry, the kind of chemistry that might have happened on Earth before life began. The Dragonfly spacecraft will not just fly past Titan, it will land and explore its surface and skies. It will look for biosignatures, which are signs that life might have existed in the past, or might still exist. By flying from place to place like a drone, Dragonfly will study the moon's atmosphere, icy ground, and mysterious organic materials that cover it. The goal is to find out whether Titan, even though it is far from the sun and very cold, could still be home to life. Another amazing mission is the Europa Clipper, which will explore Europa, one of the smaller moons orbiting Jupiter. This spacecraft is set to launch in October 2024, and it should reach Europa in April 2030. Instead of landing, Europa Clipper will fly by the moon many times to collect data. Its main goal is to find out if Europa, covered in thick ice, could have a liquid water ocean under the surface, and whether that ocean could support life. Scientists are especially interested in Europa because they think under its frozen surface there is a large, salty ocean. This hidden ocean might hold 2 to 3 times more water than all of Earth's oceans combined. Here is some evidence that supports this idea. In 1979, NASA's Voyager 1 spacecraft took the first close-up pictures of Europa. The images showed strange surface features that looked like cracks or ridges, similar to tectonic activity on Earth. Scientists thought this could be caused by an ocean below pushing and shifting the ice above. In 1997, NASA's Galileo spacecraft noticed a small change in Europa's magnetic field as it flew past. This was taken as a strong hint that something that conducts electricity, like a salty ocean, was hiding under the ice. Then, in 2012, the Hubble Space Telescope saw something amazing, a giant plume of water vapor shooting into space from Europa's surface. This suggested that water from the ocean below might be escaping through cracks in the ice. The Europa Clipper will carry special tools to study this further. It will try to confirm if the ocean really exists, find out what it is made of, map the icy surface, and look for any signs of activity from the deep ocean. All of this could help answer the big question: could life survive there? Now let's talk about another moon with a hidden ocean, Enceladus, a small moon of Saturn. While there isn't a mission yet to look specifically for life on Enceladus, this moon has shown amazing signs that make scientists curious. In 2005, NASA's Cassini spacecraft saw jets of water vapor shooting from cracks near Enceladus's south pole. These geysers were later found to contain salt and organic molecules, the kind of chemicals life might need. Then, in 2014, more detailed measurements supported the idea that a large underground ocean exists beneath Enceladus's ice shell. Because of this, many scientists hope future missions will visit Enceladus to look for life. But what about life outside our solar system? The closest potentially habitable planet beyond our Sun is called Proxima Centauri b. It orbits a star only 4.2 light-years away. In space terms, that's very close. But even at that distance, with today's spacecraft technology, it would take more than 18,000 years to get there. That means we can't visit it anytime soon. Instead, scientists use powerful telescopes to study planets like Proxima Centauri b from far away, hoping to see signs that life might exist there. So far, scientists have not found confirmed signs of life on exoplanets, planets outside our solar system. However, this field is growing fast. A big step forward came in December 2021, when NASA launched the James Webb Space Telescope. While the Webb telescope cannot detect some important gases like oxygen in exoplanet atmospheres, it can still find clues, such as chemical patterns or temperature changes, that might hint at life. Looking ahead, new telescopes being built on Earth, like the 30-meter telescope and the extremely large telescope, will let scientists study distant planet atmospheres in much more detail. These giant telescopes will help separate real signs of life from false signals, such as oxygen made by things other than living creatures. At the farthest edges of the part of space we can see, there are some truly amazing and puzzling things happening, things that help us understand just how big, strange, and beautiful space really is. The observable universe is like a giant bubble around us. This bubble stretches as far as light has been able to travel since the universe began, about 13,800 billion years ago. But this outer limit is not a wall or an edge in the usual sense. Instead, it is more like a horizon, a boundary that shows us how far we can look based on the age of the universe and the speed of light. Near this edge, space is full of strange and powerful events that help us learn more about how everything started. One of the most important things found near this boundary is something called the cosmic microwave background radiation. This is a faint glow of light that fills the whole universe. It is like the leftover heat from when the universe was just born, just after the Big Bang. You can think of it like the soft afterglow from a fire that has just gone out. Even though this light is very weak now, it carries important information. It shows us what the universe looked like when it was only about 380,000 years old, a time when it was still hot, thick, and full of tiny particles swirling around. By studying this ancient glow, scientists can figure out what the universe was made of, how it grew, and what its early moments were really like. As we look farther out into space, we also see galaxies moving away from us at amazing speeds. This happens because space itself is stretching in all directions. The farther away a galaxy is, the faster it seems to be moving away. Some galaxies are so far out that their light will never reach us, no matter how long we wait. That means there are huge parts of the universe we will never see, regions full of stars, planets, and energy that will stay hidden forever. Another strange effect seen near the edges of the observable universe is redshift. As galaxies move away, the light they send out gets stretched into longer waves, which makes it look redder than it really is, just like the sound of a car engine changes as it drives past you. This change in light tells us how fast the universe is growing. The more redshift we see, the faster the object is moving away, and the farther back in time we're looking. At these great distances, we can also spot giant structures that are still forming or are barely visible. These include faraway galaxies, huge webs of matter called cosmic filaments, and large clusters of galaxies held together by gravity. These structures show us the forces at work in the universe, slowly shaping everything over billions of years. The edge of what we can see is not empty or quiet. It is full of mysteries and clues. It helps us understand how the universe started, what it is made of, and even where we might be going in the future. But there is more to this story. Some of the strangest and most powerful things in space are black holes and quasars. These objects remind us that the universe is full of surprises, many of which we still do not fully understand. A black hole is a place in space where gravity is so strong that nothing, not even light, can get out. It is like a bottomless pit in space. Because no light escapes, we cannot actually see the black hole itself, but we know it is there because we can see what happens around it. When gas, dust, or even stars fall toward a black hole, they spiral in like water going down a drain. As this material spins, it heats up and shines brightly, sometimes brighter than whole galaxies, before it disappears into the black hole forever. This glow gives us clues that a black hole is nearby, even though we cannot see the hole itself. Quasars, on the other hand, are some of the brightest things in the whole universe. A quasar is powered by a supermassive black hole at the heart of a galaxy. As material falls into the black hole, it releases a huge amount of light and energy. Quasars shine from incredibly far away, billions of light years out, so we are seeing them as they were long ago when the universe was still very young. They help us study how galaxies formed and grew at the very edges of what we can see. But black holes and quasars also suggest there may be even more waiting to be discovered. They hint at distant areas filled with strange matter and forces we have not yet seen or understood. They remind us that most of the universe is still a mystery, and the more we learn, the more there is to explore. Another amazing part of the universe's structure is something called galactic superclusters. These are like giant cities of space. Just as cities are made of many neighborhoods, superclusters are made of many galaxy clusters, each filled with galaxies, stars, planets, and other cosmic objects. These superclusters are the largest known structures in the universe. If we think of the universe as a massive web, then the superclusters are the knots where many threads meet. They are held together by gravity and connected by strands of dark matter, which is an invisible material that we cannot see but know is there because of how it affects other objects. Superclusters also shape how galaxies move. Their gravity pulls galaxies along like roads guiding cars. In this way, superclusters help organize the universe. By studying how these giant structures formed and how galaxies are spread out within them, scientists can understand how the universe grew over time. Superclusters even give us clues about dark energy, a mysterious force that is pushing the universe to expand faster and faster. So, galactic superclusters are not just random piles of galaxies. They are important parts of the universe's blueprint, helping shape everything we see and helping us uncover the story of how the cosmos came to be. Then there are cosmic voids and filaments, two opposite but equally important features that help shape the universe on a huge scale. Picture the universe as a vast web. The filaments are like glowing threads, made of galaxies and dark matter, stretching across space and connecting everything. These filaments act like highways for galaxies, guiding how they move and gather together. In between the filaments are the voids, huge, empty areas with very few galaxies. Even though voids may seem boring, they teach us a lot. These empty regions are growing faster than the crowded ones, and they help scientists understand how the universe is expanding and changing. Light from faraway galaxies bends as it passes through different areas of space, including filaments and voids. This bending of light helps astronomers measure distances and map out the universe more accurately. Together, filaments and voids show us the real shape of the universe. They reveal how matter is spread out and how everything is linked by invisible forces acting across enormous distances. but the most mysterious parts of the universe might still lie far beyond what we can see. One of the biggest mysteries is something called dark matter. It makes up most of the mass in the universe, but we cannot see it because it does not shine or give off energy. Scientists know it is there because of how it affects how galaxies move. Without this hidden matter, galaxies would spin apart, so dark matter is like an invisible framework holding everything together. Then there is dark energy, another invisible force, but one that works the opposite way. While gravity pulls things together, dark energy pushes things apart. It is the reason why galaxies are moving away from each other faster and faster. No one really knows what dark energy is, but we can see its effects across the universe. Some scientists even think there could be extra dimensions, more than the 3 dimensions of space and 1 of time that we are used to. These other dimensions might hold new types of particles, strange forces, or even other universes with different rules of physics. At the smallest scales, even empty space is not really empty. Thanks to quantum physics, we know that tiny bursts of energy, called quantum fluctuations, are always popping in and out of existence. These little bursts might help us understand the deeper layers of reality. All of these wonders, from glowing aftershocks of the Big Bang to the invisible powers of dark matter and energy, show us that the universe is far bigger, deeper, and more mysterious than we ever imagined. Every discovery we make only leads to more questions. That endless journey of curiosity is what makes exploring the cosmos such an exciting adventure. To go beyond the part of the universe we can see, people face the huge challenge of understanding the edges of space and time itself. The part of the universe we can see is like a giant dome around us, shaped by how fast light travels and how old the universe is. Beyond this edge are parts of space that we not only can't see but may never be able to reach. First, let's think about the speed of light. It's the fastest speed anything can go in the universe. Nothing can move faster. Since light from faraway galaxies takes billions of years to reach us, we can only see those parts of the universe where the light has had enough time to arrive. To travel beyond this visible area, we would need to either break that speed limit or find a way to bend space itself. One idea that's been suggested is bending space, kind of like folding a piece of paper to bring 2 far apart points closer together. This idea, often called a warp drive, would, in theory, let a spaceship squeeze space in front of it and stretch space behind it. That way, it could travel huge distances without breaking the speed limit of light in normal space. Another thing to think about is that our universe is not still. Space is growing, and galaxies are moving away from us. Some areas are moving away so fast that their light will never reach Earth. To get past the edge of what we can see, people may need to build new tools that can detect or reach parts we can't see. Maybe using very advanced machines that can sense changes in gravity or the leftover light from the early universe. Also, we have to deal with the big problems that come with long space trips. This includes systems that keep astronauts alive, shields from harmful space radiation, and making sure the spaceship can survive the stress of such a long trip. Human missions to faraway stars give us just a small idea of what's needed. In the end, going beyond what we can see in the universe needs not only new technology and clever ideas in science, but also a whole new way of thinking about space. It calls us to imagine a future where our drive to explore and create helps us go past what we know today, maybe even finding places and things we never thought were possible. The idea of going faster than light sparks the imagination and brings up some really exciting thoughts. Scientists and thinkers have talked about a few what-if technologies that could make this dream come true. One of the most well-known is the idea of a warp drive. Picture a big bubble surrounding a spaceship. This bubble would bend space by shrinking it in front and stretching it behind. This would let the spaceship ride a wave of bent space, moving faster than light compared to the space outside the bubble, without breaking the rules of physics. Another amazing idea is that of wormholes. These are like tunnels in space and time that could link 2 faraway places in the universe. If we could make one or keep one stable, then moving from one end to the other might happen almost instantly. But making a wormhole would be very hard. It might need a strange kind of matter with negative energy, something we haven't found or fully understood yet. Some people also talk about using strong magnetic forces to push a spaceship really fast. This idea, called electromagnetic propulsion, is still far from real, but as we improve these systems, we might get closer to making it work. There's also something called time stretching, or time slowing down. Even if we can't go faster than light, if we move close to that speed, time would slow down for the travelers. A trip that takes many years could feel short to them. That could help them cover great distances in ways that change how we think about space travel. Even though these ideas are still just theories, they show some of the paths people might take to explore space in ways we're only starting to imagine. Each idea needs more research and big scientific steps forward, but they give us hope for a time when the stars won't seem so far away. Going into parts of space we've never been to is a journey full of both wonder and big problems. One of the biggest is how huge space is. Picture being in a place so big that even if you travel at amazing speeds, it could still take many years or even hundreds of years to get there. These giant distances make planning a trip very hard. It's not just about choosing the right path, it's also about having enough fuel and supplies for the whole trip. Another big danger is radiation. Out in space, there's a steady stream of harmful energy and tiny fast particles coming from stars, cosmic rays, and other space events. This radiation can hurt people and break parts of the spaceship. Astronauts need strong shields and careful planning, because being around this radiation too long could be very risky for their health. Then there's the problem of low gravity. Even though it sounds fun, living with very weak gravity for a long time can be bad for the body. Muscles get weaker and bones can lose strength. To stay healthy, astronauts need special workouts and diets while they're on long missions. Mental health is also a big concern. Being alone, stuck in a small space, and looking out at the empty darkness of space can make people feel lonely and stressed. On very long trips, keeping astronauts in a good state of mind is just as important as keeping their bodies healthy. Good support systems and fun activities are needed to fight off these emotional problems. Another serious problem is when machines stop working. No matter how high-tech a spaceship is, things can still go wrong. Imagine being far from Earth and having something important break. That's why engineers have to build backups and train astronauts to fix problems fast when things go wrong. Also, unknown places in space come with their own dangers. Things like extreme heat or cold, strange air, or rocky, unexplored land can be very risky. Sudden natural events, like meteor showers or strong bursts from the sun, could be dangerous too, and the crew would need to act fast. The challenges of exploring the parts of space we've never been to are huge. They include finding your way across giant distances, staying healthy, keeping spirits up, fixing problems with technology, and dealing with unknown space dangers. Each challenge needs serious planning to make these space journeys not just possible, but also safe and successful. Wormholes and warp drives are two amazing ideas in science that offer exciting ways to go beyond the limits we have now. Both suggest ways we might skip the huge space between stars and galaxies. Wormholes can be thought of as shortcuts through space and time. If you picture the universe as a flat surface, like a piece of paper, a wormhole would be like punching a hole in it and creating a bridge from one far spot to another. Instead of travelling the whole long way, you could go in one end and come out the other, jumping across space in a moment. But this idea is not simple. A working wormhole would need special conditions like strange matter with very different properties from anything we know so far. Warp drives are another exciting idea. Instead of making a tunnel through space like a wormhole, a warp drive would stretch and squeeze space itself. Imagine the universe as a cloth, and the warp drive makes a ripple in it, pushing the spaceship forward. It squeezes space in front and stretches it behind, letting the spaceship move faster than light without actually going that speed through normal space. But building a warp drive would need super advanced tools and maybe materials or energy types we haven't discovered yet. Both wormholes and warp drives test the limits of what we know about how the universe works. They make us wonder what else is possible. Scientists are still thinking about these ideas and trying to understand them better, asking big questions about space, time, and how people might someday travel far beyond our solar system. The drive to understand these ideas helps push us forward as we search for ways to leave Earth and explore the stars. Looking for life in places we can't see yet is one of the most exciting parts of space science. As we look beyond our own planet, the huge size of space gives us so many chances to find life in forms we haven't imagined yet. The universe is unbelievably big, with billions of stars and even more planets. Many of these planets might have the right conditions for life. First, we need to think about life that might be very different from life on Earth. Life here needs water and carbon, but scientists think there could be life that uses other chemicals or lives in extreme places. For example, some moons in our solar system, like Europa and Enceladus, might have oceans under their ice, and those oceans could have tiny living things. Looking even farther, the discovery of planets outside our solar system, called exoplanets, has made the search for life even more exciting. Some of these planets are in the just right zone, where water could stay liquid. If they have air and the right chemicals, they might be able to support life, even if we haven't seen it yet. Also, the universe is always changing. As it grows, new parts come into view, and with better tools, like stronger telescopes and new space missions, we keep learning more about faraway places. Every time we find things like simple organic molecules or strange gases on distant worlds, it makes us more hopeful that life is out there. Even though we haven't found life beyond Earth yet, the chances are big. Every new discovery and our better understanding of how life can survive in different places brings us closer to finding it. Somewhere out there, in the wide, star-filled sky, life could be waiting for us to find it. Gravity and microgravity effects, especially how reduced gravity changes matter and life, form one of the most fascinating areas of space science because they reveal what truly holds the physical world together. Gravity is the quiet force that keeps everything on Earth anchored. It keeps oceans from floating away, it keeps the air wrapped around our planet, it pulls raindrops to the ground, and it gives weight to every object we hold. Gravity can feel ordinary because we grow up with it and feel it every second, yet without it, the world would collapse into chaos. To understand reduced gravity, often called microgravity, one must appreciate how this invisible force controls the tiniest particles in our bodies and the largest movements of planets. On Earth, a person drops a stone, and the stone falls with a steady pull because gravity never stops acting. In space, that same stone could float freely, drifting slowly because the pull becomes extremely weak. This state of reduced gravity does not mean there is no gravity at all. Gravity exists everywhere. Even far from Earth, the pull of our planet can still reach astronauts, but it is extremely small. Microgravity is a condition in which objects fall continuously around Earth, rather than plummeting to the ground. Astronauts orbiting Earth experience microgravity because their spacecraft is constantly falling toward the planet while also moving forward fast enough to keep missing it. This creates the feeling of weightlessness, even though gravity is still present. Living in microgravity changes almost everything, from the behavior of liquids and gases to the behavior of bones, muscles, and even the way the human heart beats. Since life has developed on Earth under one constant pull, reducing that pull alters natural processes in surprising ways. People on Earth rarely think about how important gravity is to shape the human body. Our bones are strong because they carry our weight. Our muscles stay firm because they constantly work against the downward pull. Our hearts pump with a certain force because they must push blood up against gravity to reach the head. When gravity becomes nearly zero, all these natural systems behave differently. One of the earliest things astronauts notice in reduced gravity is a shift in body fluids. On Earth, gravity pulls fluid downward, causing more blood and water to gather in the legs. That is why feet swell after long hours of standing. In space, this does not happen. Fluid spreads more evenly through the body and moves upward. Faces puff up, legs become thinner, and astronauts sometimes feel congested as though they have a mild cold. This happens because the body becomes confused. It senses too much fluid near the upper body and tries to correct it by producing more urine. Over time, this can lead to dehydration and a loss of blood volume. This is one reason astronauts need to drink more water and take special health precautions. Bones also respond dramatically. Without gravity pressing down on them daily, bones begin to lose minerals, especially calcium. On Earth, this would take decades, but in microgravity, bone loss can happen in a few months. Some astronauts lose as much as 1% of their bone mass every month they spend in reduced gravity. This is similar to the bone loss older adults experience on Earth, but far faster. The body senses that the skeleton is not needed for heavy support and reduces its strength. To slow down this loss, astronauts exercise for hours every day while in orbit, using special machines that create resistance even in the absence of gravity. Without this, their bones would weaken severely. Muscles face a similar issue. Think about the constant work muscles do on Earth. Just standing upright requires strength. The back muscles support the spine, the legs hold the body up, and the core muscles stabilize movement. In microgravity, these muscles get a long break, and the body quickly adapts by shrinking them. This is called muscle atrophy. Astronauts who spend long missions on the International Space Station must exercise regularly to maintain their strength. Even with exercise, muscles remain weaker upon return to Earth, and astronauts often find walking difficult during their first days back. Their bodies must relearn how to live with full gravity. Reduced gravity affects the heart too, though in a more subtle way. The heart no longer needs to work as hard to pump blood upward, so it gets smaller and less powerful. This is similar to what happens to athletes who stop training for a long period. Their hearts shrink slightly because they are not pushed to perform daily challenges. When astronauts return to Earth, their hearts need to rebuild strength to pump blood against the full pull of gravity again. Some astronauts feel dizzy when they stand up because their bodies struggle to keep blood in the upper body instead of allowing it to rush downward. This is why astronauts often undergo medical tests before and after missions, to track how their hearts respond to microgravity. Reduced gravity affects matter just as strongly as it affects biology. Liquids form perfect spheres in microgravity because surface tension becomes the strongest force acting on the liquid. On Earth, gravity shapes water into droplets that fall, splash, and flatten. In orbit, water floats as round bubbles that drift slowly. This behavior requires astronauts to be careful with fluids because a single loose bubble of water can damage electronic equipment or drift into someone's face. Astronauts drink from sealed pouches using straws designed to control the flow of liquid. In reduced gravity, flames behave differently as well. On Earth, hot air rises because gravity pulls cooler air downward, pushing warmer air upward. This creates the familiar shape of a tall flame. In microgravity, hot air does not rise. Flames become small blue spheres that burn slowly and can even extinguish themselves if they do not get enough oxygen. Fire behaves unpredictably in space, so the International Space Station uses special equipment and safety protocols to prevent accidents. Microgravity changes how materials mix too. In normal gravity, heavier materials sink and lighter ones rise. In reduced gravity, materials no longer separate naturally. This can be useful for experiments. Scientists can mix substances in microgravity in ways that cannot be done on Earth. For example, some experiments on the International Space Station focus on growing crystals. These crystals grow more perfectly in microgravity because they do not settle or sink. This research has helped scientists develop better medicines and stronger materials. Even plant growth changes without gravity. On Earth, plants grow upward because gravity pulls their roots downward, and the stems grow in the opposite direction to reach sunlight. In microgravity, plants lose this sense of direction. They rely more on light to guide their growth. Roots grow in random directions and stems may twist in unusual ways. Though plants can grow in space, farmers on Earth rarely encounter such behavior. Experiments on plant growth in orbit are important for future space missions, because long-term journeys will require astronauts to grow their own food. Reduced gravity plays an essential role in understanding the limits and adaptability of living things. Scientists study microgravity to uncover how cells behave when relieved from Earth's constant pull. Many discoveries from these studies help medicine on Earth. For example, the rapid bone loss astronauts experience in orbit provides insight into bone diseases. Understanding how bones weaken and how they can be strengthened helps researchers develop new treatments for people suffering from bone loss. Studying muscle atrophy in space also contributes to rehabilitation treatments for patients who cannot move for long periods. Microgravity research even teaches us how bacteria behave differently. Some bacteria grow faster in reduced gravity because they feel less stress and spread more easily. This can help scientists understand how to prevent infections in hospitals and other environments. It also helps design safer space missions by identifying which bacteria become more dangerous in orbit. The human brain is not left out of these changes. In microgravity, sensory signals become confused. On Earth, the inner ear senses movement and orientation by using tiny crystals that shift under gravity. This helps us know what is up and what is down. In reduced gravity, these crystals do not settle in any direction, causing the brain to receive mixed signals. This leads to space sickness during the first few days in orbit. Astronauts may feel dizzy or nauseous until their brains adjust. After adjustment, some astronauts report that moving in microgravity feels natural and even enjoyable. However, Once they return to Earth, the confusion happens again until the brain readapts to full gravity. Reduced gravity affects how the human spine behaves as well. Without the constant downward pull pressing the vertebrae together, the spine lengthens slightly. Some astronauts grow about 5 centimeters taller in orbit. This does not cause pain in space, but once they return to Earth, the spine compresses again, sometimes causing temporary discomfort. Understanding microgravity is essential for planning future space missions that may last years rather than months. Missions to Mars, for example, require astronauts to travel for many months in microgravity before reaching a planet with only about 1/3 of Earth's gravity. If astronauts arrive with weak bones, shrinking hearts, and disoriented brains, they may not be able to carry out their tasks safely. This is why scientists design special training programs, exercise machines, and protective environments inside spacecraft to reduce the harmful effects of microgravity. Even the way metals form and behave changes in reduced gravity. On Earth, molten metals separate based on weight, but in microgravity they blend more evenly. This helps researchers explore how to create alloys with new properties. Manufacturing in space may one day lead to stronger or lighter materials that cannot be produced on Earth because gravity interferes with their formation. Reduced gravity is not just a challenge, it is also an opportunity. It provides a unique laboratory that cannot be recreated on Earth, except for a few seconds during special flights or experiments. Scientists use the International Space Station as a long-term research platform to conduct experiments that are impossible under normal gravity. These studies help answer questions about how life forms adapt, how matter behaves, and how the universe functions. Every discovery in microgravity deepens our understanding not only of space, but of our own planet. The effects of microgravity even reach into psychology. Living in orbit means living in a confined space with limited personal room. The absence of weight changes how people move, sleep, and interact. Some astronauts find it peaceful, while others find it stressful. The human mind is shaped by gravity as much as the human body. Without a clear sense of up or down, daily routines require careful planning. Simple tasks such as eating, sleeping, or cleaning become complex without a stable foundation. Astronauts must strap themselves to their beds at night to keep from drifting away. Meals must be eaten carefully to prevent food from floating into equipment. Tools must be attached to surfaces or they drift out of reach. Reduced gravity affects the feeling of time as well. On Earth, rhythms like walking, waking, and lying down structure the day. In microgravity, movement feels effortless, and daily tasks do not follow familiar patterns. This can confuse the brain and sometimes lead to sleep problems. Special lighting is used on spacecraft to help astronauts maintain their sleep cycles. Gravity not only shapes life, but also shapes the human sense of identity. People grow up learning how to move, stand, sit, and balance. Microgravity removes this foundation and replaces it with new rules. Astronauts must adapt both physically and mentally to a world where traditional ideas of weight, balance, and direction no longer apply.